to make me happy, it has to be an anti-aging drug, and the evidence has to be effects on many different age-sensitive properties. But we have great evidence now for at least 3 mutants, and the calorie restriction diet, and the methionine restriction diet, and we're getting there for rapamycin and several of the other drugs that came along, 5 years, 8 years after that. So I think there will be a very strong case that these drugs are acting by slowing the aging process and delaying, maybe not quite all, but maybe all of the aspects of aging that make people unhappy about getting older.
Hey everyone, welcome to the Drive Podcast. I'm your host, Peter Attia. Hey Rich, great to sit down with you again. I don't remember exactly when we did this before, but I know I enjoyed it thoroughly, and it's actually one of the few podcasts I've gone back and listened to. I don't often, for obvious reasons, go back and listen to podcasts that I've recorded because I already heard them, but there was so much in that one that I've at times gone back and listened to parts of it. So excited to sit down and chat with you again. Assuming that maybe people who listened to us in the past, or maybe even aren't familiar with the ITP, I think it's always great to start with sort of an overview of what the interventions testing program is. I certainly refer to it a lot in both podcasts and even in things I write.
Sure. It was developed by the National Aging Institute under the leadership of Hubert Warner about 20 years ago. We are just now finishing our 20th year. And we've sent in applications, so if the peer reviewers like it, we may get 5 more years of funding. It represents work being done by 3 different research laboratories, mine at the University of Michigan, Randy Strong's at the University of Texas Health Science Center at San Antonio, and a program at the Jackson Labs where David Harrison was in charge. David will be stepping down next April, and he will be replaced by Ron Korstanja as the first new appointment for the ITP leadership at the Jackson Labs. What we try to do is quite simple. We try to find drugs that will slow aging and extend mouse lifespan. We have a national announcement every year, international. Anyone who wants to suggest a drug sends us an application, and they tell us why they think we should test their drug and why they think it will be good and not hurt the mice. We have a committee that evaluates those, and then we pick 5 or 6 or 7 each year to see if indeed giving them to the mice will give them a lifespan extension. We've had 4 published significant hits and another 2 or 3 that are significant, but really small, and another 2 that are in press that should be, I hope, accepted soon. So this gives us a range of successful drugs, and we can then, and we do, try again. We give them to mice at varying doses to see if it's dose sensitive. We look at the pathology. We make tissues that we can give away to other investigators for collaborative studies. And we try to reason about mechanisms of aging and control points for aging based upon which drugs work and which drugs don't work. A lot of people see this, and I can understand that. I agree with this as a stalking horse for the important goal of finding drugs that would extend lifespan by slowing aging in people. And that is an important element, but there are many steps between a mouse drug and a human drug. The other major things that our program does is it really gives us a lot of insight into the biology of aging, which in the moderate term should give us many clues as to what to look at that may be successful.
There's a lot in there that I want to kind of talk about, Rich. So I think I'll start with just a couple of simple questions. First, in a given year, how many candidates do you typically get nominated?
It varies a lot from year to year. This year was our winner. We had 28 suggestions, and we only have enough money to do 5 or 6 or 7 of them. In a typical year, it's 10 to 15, from which we pick about 6 annually. Sometimes we fill up those slots with things that we want to do. For instance, we found a couple of years ago that a drug, Captopril, which is FDA approved in people for blood pressure, kind of to my surprise, gave a really small increase in lifespan in mice. Mice don't die of hypertension, they don't get strokes, etc. So I was betting against that, but it was a really small effect. So we decided in the current year, try Captopril again, but at a higher dose. Maybe it'll work give us a nice big effect if we use a higher dose. Some of those slots each year then are taken up with other doses, other dosage forms. Often if a drug works when you give it to young adults, we say, okay, great, now let's test it in middle-aged mice. Everyone would like to know, as we would, of course, whether a drug would only work if you give it to young adults. We would love to find drugs that work in middle age as well. So that's often fills up one of those available slots.
Well, we'll definitely talk about a couple of those drugs. Tell me what the budget is. What does the NIA provide to the 3 laboratories?
They give $1 million a year to each of the 3 sites in direct costs. The actual cost to the taxpayer is probably about 50% more than that, because each university will also receive indirect costs to pay for the building and the heat and the police force and the library and the president and all of that stuff.
But it's basically sub $5 million a year.
About $4.5 million total per year, of which $3 million actually goes
into direct cost,
per year, direct cost to each lab,
Yeah, so again, a relatively paltry sum of money when you consider the insights that I think come out of the ITP. So maybe that's my way of lobbying for the budget being increased.
I agree. I do not think we get too little money.
Yeah.
The first 10 years we had $500,000, and the NIA thought of us, I'm pleased to say, as something that was really working well and doing good stuff. So 10 years ago, they doubled our budget. Which I think is a sign of their endorsement and their ability to recognize good stuff, and it certainly made us feel good.
What's the, and there are obviously 17 kind of divisions within NIH, of which NIA is one. What is the NIA's annual intramural and extramural budget?
Yeah, I don't know. I'd have to look that up. It's actually one of the larger institutes now. It didn't used to be, but that's misleading, because more than half of their budget goes to Alzheimer's disease. They have, through a variety of negotiations, been designated sort of the lead agency for Alzheimer's. There are good reasons for wanting to spend money on Alzheimer's research, and all of that goes through the National Institute on Aging. So their budget is big, but their budget for biology all put together is only 1/6 of the NIA budget. And for the kind of biology I care about, it's much, much less than that. A lot of the good biology is what happens to bone aging, what happens to eye aging, what happens to aging of the immune system. That's interesting research. But of course, the kind of stuff I care most about is aging as a global phenomenon. What can you do to slow aging, and how is it that aging increases your risk basically of almost everything that you don't want to happen to you? That part of the NIA budget is small.
One last question on budgeting. Is there an opportunity for philanthropic giving to plus up the NIA contributions? In other words, the $3 million in direct costs or the $1 million to each site, is there an opportunity for those numbers to go up with donations?
I don't believe that NIA accepts donations. However, a philanthropist, should he or she be listening to this podcast, can certainly set up independent arrangements. For instance, if they wish to have support for all 3 sites in the ITP, one can imagine a situation in which a foundation makes awards to each of those 3. The universities do have the flexibility to take gifts and target them to specific research groups or specific research projects, but either independently or as a consortium.
Great. Okay, let's talk a little bit about mice and men. Or I guess let's just talk about mice, actually. So one of the hallmarks of the ITP is the mouse model that is used and how it differs from some of the more typical mouse models that, shall we say, run rampant in biomedical research. Maybe tell us a little bit about what the standard off-the-shelf mouse model is, where it came from, and maybe some of the problems or limitations associated with that.
97%, the last time I checked, of requests for aged mice to the National Aging Institute were for the same kind of inbred mouse. Its formal name is C57 Black 6, and everybody calls it the B6 mouse. So these are the standard mouse, and it's a really bad thing for science, not just aging science, but science in general that relies on an inbred mouse. There are several problems. One is that it's a single genotype. And it has been shown many times now that if you have a drug that works in black 6 mice, it might work in another kind of mouse. It might not work. It might have the opposite effect in another kind of mouse. They're good, strong papers on those issues. So people study the black 6 mice in the mistaken belief that it's sort of like mice in general, despite the now really quite convincing evidence that it isn't. So the ITP, from the word go, made a decision. It was controversial, but in retrospect was a really good decision, instead to use a genetically heterogeneous mouse. The particular kind of mice we use is called het3, because that's where it was first derived, and het is for heterogeneous. These are mice essentially which have the same set of grandparents. So any 2 mice in our population share half of their genes, just like you would share half of your genes with a brother or sister. But it's a random half. So if we have 2 mice, we don't know which genes they'll share, though we know it'll be half of them, and half of the genes will be different. The advantage of the system is you can make as many of these mice as you want anywhere in the world at any time, and you'll get this year after year after year, you'll get the same population characteristics. No 2 mice are identical, but all populations of het3 genetically are identical with one another. So it's a form of reproducible heterogeneity. And this way, if we had by chance tested a drug that worked in black 6 and only tested in black 6, we really wouldn't know whether it would work in any other stock. And if we had tested a drug that failed to work in black 6, we would have fooled ourselves into thinking that it was a loser drug. Since there are thousands, tens of thousands, hundreds of thousands of genotypes available in the het3 population, it's really unlikely that one weird genotype would either trick us into believing something to be true when it really isn't, or trick us by missing a good response. The other sort of ancillary benefit is you can map genes. There's a set of collaborators, including Rob Williams at Tennessee and Johann Aurich in Switzerland, which have taken these mice. We've given them, at this point, something like 12,000 tails, 12,000 DNA samples from mice that have a known lifespan. And they have already published a paper. It came out last year in Science, and there's another one in the pipeline now that says, oh, look, here's a gene that tells you how long the females will live. Here's a gene that tells you how long males and females will live. Here's a gene that tells you how long you'll live, but it only counts if you've made it past the midpoint. It only works on the oldest half of the mice. All that is very cool science. There are hints to human genetics lying within that, and it gives you new tools for thinking about and then working out ideas about the ways in which your inheritance modifies your aging and maybe even your response to drugs.
Rich, I want to make sure that listeners who maybe aren't as familiar with genetics understand the significance of the het3 mouse relative to the black 6. So let's again talk about what it means when you have a black 6 model. They are all identical, correct?
Absolutely correct. But it's even worse than that. Not only are they identical, they are homozygous. That means that the gene they got from their mother,
the gene from the mom and the gene from the
identical.
father are the same. So it's like an inbred form of homozygosity that we don't even have a human phenotype that is that inbred.
Right. People avoid inbreeding because it turns out that when you inbreed people, you get very sick people, a lot of deaths, a lot of deformities, a lot of mental disabilities. And that's true of inbred mice as well. Inbred mice almost always have something terribly wrong with them. Nearly every kind of mouse that's used in aging research is fully deaf by 1 year of age. Many of them are blind. Many of them get a single disease, which is not representative of mice in general.
Yeah, so it's almost like a thought experiment where you take a small population of people and you make them breed and breed and breed and breed and breed until they all become one person. And then there's two issues. One is the probability that that person is healthy is 0. And then secondly, even if you accept that fact and do all of your testing, what is the likelihood that what you learn is relevant to people who are not inbred?
Yeah, you can see it in the form of a clinical trial. Let's say you have a drug, you want to test it to see if it prevents cancer in people or something, and you decide your test population will be a set of identical triplets, Jim, Josh, and John. They're identical triplets, and you've decided you're going to test it in them. People would laugh at you. That's not a good design. If you want to see if your drug works, you sort of have to test it on people who are not identical genetically to one another. Yet that sort of thing, which is so obvious in human analogies, is ignored by nearly all mouse scientists.
Yeah, I guess I hate asking people to sort of speculate on the motivations of others, but why does the Black 6 model still exist? Why is biomedical research being done in this model? If we want to have any interest in some translational insight.
You're a scientist, you're setting up your own lab, your mentor in her lab, she used Black 6. And so all your preliminary data is in Black 6. And so you do Black 6. If you are aware of these controversies, you just might say, oh, I want to test it in some other kinds of mice. But then you say, no, my money is limited. I can only afford one kind of mouse. I'm going to take the kind I'm familiar with. It's like lemmings. You follow the lemming in front of you because that's just how lemmings do it. They don't look at a road map or think about the optimal path to take. They just follow the person who trained them, who's following the person who trained them, et cetera, et cetera. Inbred mice are good for two things. They're almost always sick. And if you want to study some kind of sickness, bingo, you've got it. If you want to study lymphoma, you've got some inbred mice that get lymphoma or get blind or get hereditary deafness or something. Studying inbred mice is great for that. The other thing that they're critical for is for transplantation. There are a lot of experimental designs where you have to take cells from one kind of mouse, stick it into another kind of mouse. For that to work, both mice have to have the same genotype. Inbreds are still bad for that. The right ones you want to do are the children of two different kinds of inbred mice. That's called an F1 mouse. They're better because they live longer, they're less sick. But that's what inbred mice are good for. You can use them to construct real mice, like the Het3 mice. They're good building blocks, like Lego blocks. But to do science on them is almost always a mistake.
All right, let's talk about the way in which a study is conducted. So let's not necessarily even focus on a given molecule, but there's a candidate molecule that's been nominated. The board has reviewed it and decided there's enough biologic plausibility that we're going to test this. Right. Let's talk about the metrics of interest. Let's talk about median lifespan, maximal lifespan. What do those things mean? Are those always the primary outcomes? What are some of the other outcomes you consider?
The primary outcomes, the things that we do our statistics on, are the proportional hazard, that is the risk of death over the whole lifespan, which the closest easily understood term is the median lifespan. It's not quite correct statistically, but nearly always it's a good shortcut to say, see, this extended the median lifespan by 20% or 5% or whatever. The median lifespan is the age at which half the mice have died and half are still alive. So if half of the mice in the normal group died by 800 days, and in the drug-treated group, half of the mice were still alive on day 880, that's 80 days later, then that's a 10% increase in lifespan. That's a nice big jump. We also always calculate some measure of maximum lifespan. The actual maximum lifespan, the age at death of the last mouse to die, is statistically not very useful, not valid, because it varies so much depending on the population size and just the luck of the draw. What we do is a better way, which was worked out by David Allison about 20 years ago. The test statistic we use is we wait until 90% of the mice are dead in both populations, the control and the treated population. And then on the date when the 90th percent mouse dies, we say what fraction of the mice are in the treated group of the ones that are alive, and what fraction of the mice are in the control group. If we're lucky, if we have a good drug, we might have, of the mice in that pool population, if 80% of them are treated and only 20% are control, we know that we have a drug that will give you a much better chance of being alive when you're really, really old. That's the closest we can come to a statistical test for maximum lifespan.
Sorry, let's make sure I understand that again. So you have to wait until in both groups, there's only 10% or less remaining? Because that's obviously going to occur at a different time.
Yes, what you do is you make your list of all the ages of death in both groups.
Yep.
Then you figure out what age is the age at which 10% are still alive in the pool together and 90% have died in both
in the
groups
total pool. I'm sorry.
Smushed together. Yeah. So there's only one age
got it. Okay.
where 10% of the pool is still alive. Then you look at the pool and say, okay, well, what fraction of those were in the treated group? If it's a 50-50 mix, you've lost.
Yep.
If it's 80% treated and 20% untreated, you've got a winner.
Yep. Was there ever a test that looked at like the 95th percentile for each group and compared those time horizons as a surrogate or proxy for maximal lifespan? Am I making that up? It's possible I am.
You can do that. You can do the 99th percentile. There are a couple of concerns, and they're technical ones. One is that the further you push it up, 95, 99, 99.9, the fewer mice you have to work with. And so after a while, the statistical power drops. You'll miss a lot of stuff if you only have like 1 or 2 mice alive at that age. We've picked the 90th percentile because there'll still be a few dozen mice alive at that age, at the 90th percentile. The other thing you want to be really careful of is defining your test and then picking the test that looks best. We could have some groups, actually do this, though it's sort of unethical. They look at the 80th percentile, the 85th, the 90th, the 95th, and then they say, oh, it looks best at the 90th. Let's pick the 90th. That's not a good thing. You will fool yourself. You'll get false positives. And so we define arbitrarily 90th. We're going to do it at the 90th percentile all the time.
Yeah. So in other words, it's sort of pre-specified.
Yeah. Oh, you're absolutely right. It's pre-specified. It's written down before we do any test. In fact, it was written down 20 years ago.
Do you come up with a new power analysis for each experiment, or do you generally power them the same and therefore have the same number of mice in each ITP?
Yeah, we use the same number of mice in the control group and the same number of mice in the treated group each and every year. Before we start, of course, we don't know whether it'll be a good year or a bad year. Some years the mice live 5% longer or shorter than in previous years. And we also don't know which drugs will work, and the ones that do work, we don't know how big an effect they'll have. So what we've done is, with the assistance of 2 professional statisticians, and again, this was 21 years ago, we worked out the number of mice we want to have in each group, and our criterion is we wanted to have at least an 80% chance of picking up a significant result, even if one of the 3 sites had a disaster, like an air conditioning failure or a viral infection. So far, we've only had something like that happen once. But we said, let's be ultra conservative. We want to have an 80% chance of picking up an effect that's at least a 12% effect, up or down, a 2-sided test, even if only 2 sites survive. So that we use that amount to determine how many mice we're using. Now, in practice, almost always we can combine all 3 sites together. We almost never have a site-specific disaster. And that means in practice that we have 80% power to detect drugs will give us like an 8% increase or a 10% increase. 12% was kind of conservative.
And what does that amount to in total mice usage typically for a given drug? So
at each site, we are using 100 male controls and 100 female controls. So pooling, that's 300 males and 300 females in the control group each year. And for each drug, we use 50 males and 50 females, that is half as many as the controls, again at each site. So for any one drug, 50 times 3 is 150. We have 150 male mice distributed across 3 sites and 150 female mice distributed across 3 sites. We oversample the controls, that is, we double the size of the control group because we're going to compare controls to drug A, controls to drug B, controls to drug C. So in a sense, we're reusing, we're getting our best mileage out of the controls, since we can increase statistical power for every one of those pairwise comparisons by adding extra mice to the control group. So we do it that way.
In other words, if you're doing a 5-drug trial, there will be a total of 300 male, 300 female control, but there will be 750 total male, 750 total female on the combination of drugs. 150 for each.
7 drugs times 50 is 350 mice getting some drug. Yeah, male mice getting some drug.
Oh, I thought it was 150 male and 150 female per drug across the 3 sites.
Oh, yeah, you're right. I was talking about one site. At 3 sites, you're right. It's 150 times the number of drugs.
Yep. Okay. And then how much, you've done this for now nearly 20 years, what is the range or variability in lifespan, both median and maximal, for the controls?
We got something we didn't expect to see, but we've seen it almost every year for the last 20 years. We were hoping that the 3 survival curves, that is one at each site, would always be superimposable. Of course, we're all really good at taking care of mice. And for females, that was correct. Each and every year, the Michigan, Texas, and Jackson Labs female survival controls are almost always superimposable. There's been one year, 2017, where that was not the case, but most of the time it's the same. For males, however, there is a persistent and consistent difference which we really do not understand. Males at Michigan always live 5 to 10% longer than males at the other 2 sites. That's unexpected and problematic, and we really don't understand it. Maybe it's the water tastes funny, or there's some smell that the mice are obsessed about that we don't know about, or there's some contamination in the sonic environment that is site-specific. No, we've tried to do everything we can to eliminate it, and we have failed. We also know that there are site-specific differences that are read out as weight, and here it works in both males and females. The Michigan mice are always controls, are about 10% lighter, both in males and females, than mice at the other 2 sites. So despite our best efforts, we get the food from the same place, the bedding from the same place, the mice from the same place. We breed them in the same months, trying desperately to get them to come out the same way in all 3 sites. And we've gotten close, better than many people would do, but not perfect. And particularly for the survival curves in males, there's been a consistent site-specific difference.
So it's interesting that both the males and females at Michigan are 10% lighter. Presumably they're eating less or moving more, yet it only translates to a survival benefit in the males and not the females.
You have the facts right. It's the causality that's uncertain. We don't know whether the difference in survival in the males has anything to do with what's causing the weight difference. We see them both, just as you said.
Yep.
We don't know whether the changes in weight contribute to the changes in survival or whether it's just 2 independent facts. The observation that the females are lightweight too, despite the fact that the female survival curves are superimposable, suggests that it's not something simple like that.
Now, does that allow you to still pool the results for the males?
Yes, but we do it with a very standard, not esoteric statistical trick. We site stratify. That is, the survival curve for the Michigan males controls is compared to the survival curve for the Michigan drug-treated mice, and the survival curve for Texas controls to the Texas drug-treated mice, etc. And then what the statistical program does is it pools those 3 sets of results to come up with one overall statistic. In every paper, we also report separately. Here's what we saw at Michigan, here's what we saw at Texas, here's what we saw at the Jackson Labs. But our primary hypothesis, the thing that allows us to put the name of the drug with the word winner in the title of the paper, is the pooled result in which the results have been stratified. And we stratify the test for maximum lifespan, the Wang-Allison test. We adjusted that to make it stratified also.
How much complexity is there year after year, drug after drug, to create a good formulation of the drug to give the mice? How are you thinking about the dosing frequency, the dose itself, and how to ensure that the animals indeed get the amount that you want?
Yeah, that's a very good question, and we've put a lot of effort both in planning it and then executing it. The University of Texas is led by Randy Strong, who's a pharmacologist, and he has a colleague. It used to be Marty Javors, and now Brett Ginsburg has taken over that role, who devotes a lot of his time to asking exactly that sort of question. So, for example, before we give any food to mice, we make a batch of food with drug in it, and Brett's lab takes it and measures the amount of drug in the food. And if it's 5% of what we thought it would be, something has gone wrong. And so we try to work out, and this again, Brett is an expert at this, should we dissolve it first in alcohol? Should we incorporate it in the form of a corn oil suspension? What's the best way to get it into the food? So once Brett, with the involvement of Peter Reifsnyder, who runs the lab at the Jackson Labs, once Brett and Peter have shown that they can make food with the stuff in it and is at the right dose, we then give it to mice for 8 weeks. And tissues from these mice then go back to Brett. So Brett can say, yep, the tissue of the drug-treated mice has this amount of drug in the liver and this amount of drug in the plasma. So it's only at that point that we actually press the button to say, yes, we are going to use this drug in a lifespan experiment. Those pilot mice, my lab gets their liver, and we look at a batch of mRNAs because we want to at least satisfy ourselves that the drug did something. We've picked RNAs in the liver that we know are almost always sensitive to drugs. And if the drug was given to the mice and nothing happened in the liver, we start to get worried. Maybe the drug was excreted quickly and didn't have any biological effect whatsoever. And we've run into problems. I mean, the famous one, the early one, was rapamycin. About 90% of the rapamycin that was given to mice in the food never made it into the mouse because it's digested in the stomach. In the acid conditions of the stomach, it gets degraded. And so Randy, with colleagues of his, worked out a way to encapsulate the rapamycin in a capsule, a plastic capsule that makes it through the stomach and dissolves in the more alkaline conditions of the small intestine. So that was a way of tricking the body into getting the rapamycin to the portion of the GI tract where it could be absorbed. And it's not uncommon for Brett to have to say, well, you know, this is not going to work unless we dissolve it in a little bit of alcohol before we mix it into the food. So we do test for that. These are all important issues. The other thing that the data on blood concentrations, they can alert us to potential problems. For instance, many of our papers, we publish, I think, 12 papers now on rapamycin. And almost always, rapamycin has been giving a larger percentage increase in females than in males. Well, the Texas group showed that the blood concentrations are 3-fold higher in females than in males. We haven't proven that that's why the females live longer or have a greater percentage increase, but it's certainly very plausible. We've stumbled onto a similar situation with canagliflozin. Canagliflozin, we found, gave a terrific, this was published a few years ago, lovely lifespan increase, but it was in males only, not in females, which is really weird because it's a great drug for diabetes in men and women without sex differentiation. We thought it would work great in both sexes. Well, it turns out that the blood concentration in female mice is 3 times higher than in males. And as they get older and older and older, the blood concentration in the old females is 10 times the concentration of young males, and it's probably toxic. We now are going back to say, okay, well, let's give it to females at a much lower dose. Maybe that'll work. Mm-hmm. Or let's give it to females, but stop when they're middle-aged, so it won't ever reach the really high toxic concentrations. All of these assessments of drug levels allow us to be on the alert for problems of that sort and to come up with ideas for how we might solve them.
Rich, I assume it's the case that every candidate drug must be administered in the food. You're not testing intravenous drugs into muscular drugs?
Yes, this is correct. There's a footnote, which I'll get to. We could give a drug in water if there was some reason in which it wouldn't get into the food, but you could give it in the water. This would be compatible with our protocol. We can't give it to animals intravenously or intramuscularly because it's so much work to give. We have, 150 males, 150 females giving 300 shots a day or a week or a month would be a mess. In addition to which, we'd have to have a separate control group that got a saline shot. And we couldn't use regular old mice as our control. We'd have to have a separate control group to do that. You can imagine a specific situation if someone said, I've got an antibody or something. All you really have to do is give it to them once, and it will flip their immune system forever into a good configuration. please give my drug. Has to be given by injection, but only one time. We could consider that. We might need a separate once only sham group also, but I think that's the only exception to the rule that we would think seriously about.
Okay. Final question on that. Again, just so folks understand, how are you regulating the actual dose? In other words, how are you monitoring the amount of chow that's consumed, since the amount of chow that's consumed is proportional to the drug that's consumed?
We have no idea how much food any one mouse eats, and therefore we have no measurement on a mouse-by-mouse basis on how much of the drug they've consumed. We know, of course, that smaller mice eat less food than larger mice, and so they will get less drug per mouse, but probably about the same amount of drug per gram of lean body mass or something like that. There's no way to control that other than by putting individual mice in individual cages, which has its own major problems. The mice are very social creatures, and they don't like isolation cages any more than people do. And in addition, monitoring the actual amount of food a mouse eats is a fiction. No one can really do it. They can put a number down and get into the paper, but it's a fictitious number. And the reason is that mice chew their food and leave a lot on the cage, on the floor of the cage. So you don't know how much food the mouse has actually gotten into itself because you haven't measured little crumbs on the cage floor.
In total, how many drugs have been run through the protocol in the last 20 years?
I would have to go to our recent review article and then add some more drugs to it. It's about 100.
Yeah. And of course, many of those, you've already alluded to this, have been run through multiple times. So that there are many more experiments than 100. But to the point you made at the outset, there really are some notable successes. I want to talk about those. I also would like to talk about some notable failures. But let's start with the successes. So what was the first exogenous molecule that proved a lifespan extension success for the ITP?
Yeah, well, rapamycin in our 2009 paper had a really big effect. We picked a dose that seemed like it might work, and it did. It's not the optimal dose, it's less than the optimal dose, but at the dose we chose, both males and females had a significant lifespan extension. To put this into perspective, these drugs are giving like 15 to, at the middle dose, 15 to 20% increase in median lifespan. To give a sense of what that means, if you had a cure for cancer in people, no one over the age of 50 ever got cancer again, median lifespan of humans would go up by 3%. And the same is true if you had a drug that abolished heart attacks. No one over the age of 50 ever got a heart attack again. Median lifespan for people would go up by less than 3%. That's work done by Jay Olshansky and Bruce Carnes and published in Science in 1990. So the drugs that we consider, we have 4 of these now that give more than a 10% increase in lifespan in terms of proportional change of healthy lifespan are doing about 3 times better than some hypothetical drug that abolished cancer in people or abolished heart attacks in people. So that's a really significant chunk of additional healthy lifespan. Rapamycin in that first paper was also the first drug, I believe, where anyone had showed, we found, that it works quite well, even if you start in really old mice. Some of the mice that were exposed in that paper didn't start until 20 months of age, where the median survival is about 24 for males and 26 for females. It took me very much by surprise. We thought only drugs, if a drug was going to slow aging, you really do have to start it when you're young, because a lot of aging is what happens between the ages of 20 and 60 or something like that, as everyone knows. So it was stunning that a drug could start as late as that and still have a full lifespan benefit. That's really was news scientifically, and I think that's one of the reasons why the editors of Nature were interested in it. But that turns out not to be a fluke. 17-alpha-estradiol, which is male-specific, works just great if you start it at 16 or 20 months of age in the males. Acarbose, which is significant in males and females, though better for males, if you start it in middle age, it still works. It's only about half as good. Starting early is smart for acarbose, but even if you start it at 16 to 20 months of age, it still works just fine. And canagliflozin, our data in that group haven't been published yet. For males, it's still terrific. For females, as I mentioned, it actually isn't good, but we suspect it's because the drug dose, the drug concentrations in the blood of females may be toxic. So we really want to do that again, but with lower concentrations of the drug.
Do you have a sense of why rapamycin and canagliflozin are being more concentrated in females? And are you seeing that with any of the other successful candidate drugs, such as acarbose, for example, or 17-alpha estradiol, sorry?
We don't know the answers for any one of those drugs. It wouldn't be too hard to find out. You know, a pharmacologist could look at how quickly is absorbed, how quickly is it conjugated, how quickly is it excreted, does it go out in the urine, does it go out in the feces, all of that. There's very standard 50-year-old methods for answering that question. And, you know, I think would be important to address. There's a generic answer, which is really quite firmly established. The enzymes that the liver uses to deal with foreign drugs, these are called enzymes of xenobiotic metabolism, xenobiotic metabolizing enzymes, are radically different between men and women and between male and female mice. Most of them, not all, but most of them are a lot higher in females, but some are a lot higher in males, and this is also true for people. So the pace at which drugs are conjugated, put into the bile or put into the urine or excreted in the feces or excreted in the urine very often are sex specific. It doesn't surprise anyone to find that the blood concentrations may be different in men and women or different between male and female mice. The details on a drug by drug basis we haven't looked at yet. The one thing I would want to add here as a footnote is for acarbose, it has nothing to do with that. Acarbose, nearly all of it stays in the gut. It doesn't get absorbed into the body, so excretion is not the key issue. Why the acarbose has such a big effect in males and a small, significant, but small effect in females is unknown. It presumably has to do with males being more sensitive to high glucose levels. Acarbose probably works by limiting very high glucose levels, maybe for unknown reasons that triggers something horrible in the males and not so much in females.
Rich, when you talk about the difference in the pharmacokinetics between male and female mice, we can only extrapolate and say that our, cytochrome P450 system as humans must have sex differences.
Oh yeah, that's well documented, absolutely.
But what I can't tell you for the life of me, Rich, is one drug that I'm aware of that we really differentially dose in males and females beyond a weight difference. In other words, we don't seem to take into account that difference when we give a person an antibiotic or a statin or a chemotherapy. They're all based on either weight or nothing at all. And yet, I guess what I'm saying is this is kind of remarkable to me that we don't have a better set of the pharmacokinetics of these drugs and their differences in human sex and how that maybe should factor into how we think about dosing them.
I would love to see you have on your show a real pharmacologist who knows the answers to that questions. I would love to talk to a real pharmacologist and ask him or her, hey, aren't there differences between men and women in the rate at which drugs are excreted? And why isn't that informing our recommendations for drug doses in people? I think it's a really good question, but I don't know the answer.
Okay, well, that's something we're going to have to dig into a little bit because it seems like an enormous missed opportunity to get that level of granularity. You've rattled off a bunch of the successes. I think it's worth a bit of a double click on each. We can take them chronologically. So again, people who listen to this podcast are very familiar with rapamycin. Recently had David Sabatini and Matt Caberlin on together. So we did a pretty good deep dive on Rapa. But again, just on the off chance that someone's coming to this as their first exposure to rapamycin, do you remember who made that nomination for the 2009 paper?
Dave Sharp.
Okay. So came in-house almost. And the, obviously the logic at the time was what? I mean, it was 10 years earlier, the drug had been approved by the FDA for solid organ transplants. And so it was a known immune suppressant. What was the logical step that took it to, but we also think it could boost longevity?
people had just begun to make invertebrates, that is, worms and flies, with the genetic modulation of the TOR pathway. TOR is the target of rapamycin, the enzyme that rapamycin inhibits. And they were long-lived. And in fact, when you studied some of the yeast stuff that Matt Kaberlein was in on this early on with Brian Kennedy, many of the things that seem to influence yeast lifespan were also related to the TOR pathway. So Dave said, I wonder whether if you inhibited TOR in mice, they would also live longer. It really didn't have to do with the notion of immune suppression. It had more to do with control of growth and following up on the genetic data in the invertebrates. Now, in retrospect, 20-some years later, we understand that the notion of rapamycin as an immune suppressant is the sort of tip of the iceberg. There are some immune functions which it increases. There are some that it decreases. It's dose-dependent and context-dependent. By an interesting coincidence, the same year that our lifespan paper appeared, there was another paper where, also from Michigan, though not my lab at all, in which they gave rapamycin to some old mice and shown that their influenza vaccine response was terrific if they'd had rapamycin. What rapamycin appears to do in their model is it increases the production of B cells from the bone marrow. So the mice would respond to influenza vaccine, and then they were exposed to live virus and they survived, whereas the untreated controls did not survive. So in some circumstances, at least, it's actually immunoboosting.
And that was also demonstrated by Joan Manick and Lloyd Klickstein 6 years later, using everolimus.
Yeah, it improves, that's right. In humans, it also improves vaccine responses in some circumstances to influenza and vaccination in humans.
Yeah. So you've already alluded to this, but I think it's, again, just worth making sure folks understand this. You had a little bit of a challenge getting the rapamycin formulated. Why did you decide not to abort the study? When you finally got the food formulation done, you've got these geriatric mice. You finally get to start feeding them rapa. I mean, obviously, chance favors the prepared mind, according to someone famous. You elected to take a chance. Do you remember the decision? I mean, the odds were long, right?
There are two decisions. Yeah. Step one was Randy Strong saying, I'll bet we can get this into mice. I've got buddies who do encapsulation. Let's encapsulate it and see if that stuff works. So Randy's initiative and creativity were the first important step. Now we have a batch of mice. They're 20 months of age. They were originally going to get rapamycin when they were 4 months of age. We could either A, throw them out, or B, give them the rapamycin. So we picked B. We were sure it wouldn't work. Now we were wrong. So when Randy finally, with his colleagues, figured out how to make the protected version, the encapsulated version of rapamycin, we actually used it twice. The same batches. Some of it went to the mice that were already 20 months of age, so we wouldn't have to throw them out. And then we gave the rest to the young mice that had been produced in the following year, expecting that the old mice, it would fail, the young mice, it might work. And as you know, it worked well in both ages.
What was the difference between the male females in the 20-month onset versus the 4-month onset, both by sex?
Scott Pletcher actually did that analysis. When you compare within sex, so you're comparing older females to younger females, there's no difference, surprisingly. The benefit you get starting in old age and the benefit you get starting in young mice is statistically insignificant in females, and it's statistically insignificant in males. In both sexes, starting as late as 20 months of age does not diminish the ability of the drug to extend lifespan.
This is just really remarkable. What do you, I mean, let's try to philosophize a little bit about what that tells us about the biology of aging, or does it tell us more about aging, or does it tell us more about the drug?
Well, I think it tells you something about both, about the drug and its interaction with the aging process. The sort of inevitable conclusion, which I would have bet a lot of money against, is that by the time you're 20 months of age in a mouse, which is sort of like 55 or 60 years old in a person, something like that, not yet at the median survival, but getting pretty close, that damage will have occurred that's irreversible. collagen cross-linking and death of some brain cells and clogging of the arteries or whatever's going to get you. It started already by the time you're in your 50s and 60s, or for a mouse, by the time you're in your 20th or 21st month. But apparently there's still some further stages of that process that occur afterwards, after we started to administer the drug at 20 months of age, which are dependent on aging, and the drug inhibits. So that's the news that we would not have known if we hadn't done an experiment starting in late middle age. Now, what those processes are, whether they are the same processes as affected by many different drugs, that's unknown. If we have time at some point to talk about these new aging rate indicators that has come out of the ITP program, we can begin to ask questions about whether the aging rate indicators are effective in the old mice or the middle-aged mice or the young mice. Clearly, we've got a lot to learn now about what is happening that is drug sensitive even in middle-aged mice. The fact that acarbose works half as well in middle-aged mice, canagliflozin works, at least in males, quite well in middle-aged mice, which is unpublished, and that 17-alpha-estradiol works great even in middle-aged male mice, suggests that it's a general phenomenon. It's not rapamycin only, but it applies to a lot of phenomena. Mike Garrett, when he was in my lab, he's now set up his own lab in New Zealand, but he took a lot of mice and he put them on 17-alpha-estradiol or acarbose in middle age, and he found, and this is all published, that their grip strength is great, much better than untreated old mice, and their ability to stay on a rotating rod, which is a complex phenomenon having to do with balance and muscle strength and motivation, that is much better even if they started the 17-alpha-estradiol or acarbose in middle age. It's not just a matter of the things that are going to kill you. These mice don't die of dizziness or loss of grip strength or something, but a whole batch of stuff that is age sensitive is slowed by these mice. The next frontier that I really want our lab and other labs in the ITP to dive into is cognition. Michigan has just recruited an absolutely top-notch mouse neurobiologist, a woman named Catherine Kazarowski, and we already have several studies planned or underway in which we're going to be treating mice with these drugs, and in addition to looking at their lifespan, test them for cognition. The obvious hypothesis is that the drugs that extend lifespan will also postpone loss of cognitive function. For complicated reasons, Catherine thinks that will be untrue, and I think it is true. So we'll see which of us is correct.
What other measures of health span are you capturing? Obviously, cognition is a piece of health span, but you already mentioned grip strength and then some complex motor tasks and some complex stamina tasks. Do you look at, for example, muscle mass at the time of demise in these mice, though it's, not a direct driver of health span, it's a highly correlated driver of health span. I mean, what else can you say about these mice and their health beyond just the elongation of life?
Right. So we have stage 1 and stage 2 studies. In a stage 1 study, which we do for every new drug, lifespan is the only thing we measure in addition to body weight at 4 ages. We could throw in other tests, but it's really expensive to do that, and to standardize it so that all 3 labs get the same numbers proved to be really tricky. So if we did devote lots of our efforts to looking at these secondary measures of health, in addition to lifespan, we would test only 3 drugs a year, maybe 4 drugs a year.
But once you've got candidates,
Once we've got candidates, yes, then we go into stage 2. Every drug that makes it to stage 2, we develop a protocol that takes advantage of the strengths and weaknesses and interests of each site. So Dave Harrison, for instance, had many tests of visual acuity, hearing acuity, strength, body temperature regulation. So the stage 2 experiments at the Jackson Labs incorporated many of those tests. Randy Strong and his colleagues were interested in glucose control and glucose homeostasis. So the stage 2 stuff that was done at Texas always had some taste of that. my lab is interested in pathology. So we would take a lot of these stage 2 mice, euthanize them at 22 months of age, send them to a veterinary pathologist, and come back with a long list of, here's what's happening in the liver, but look, it didn't happen in the drug-treated mice. Here's what's happening in the gut, but look, it didn't happen in the drug-treated mice. So our other hope, of course, is that once we have a winner, the laboratories that have a specific interest in aging of the aorta and aging of the heart and aging of the lung, and who know what they're doing, will just ask us for tissues. Either they can buy the drug and treat their own mice, hopefully not black 6, but they can treat some mice, by CAT3 mice, with the drug and test their organ-specific functional or pathological outcome tests. Or if we have tissues in our freezer, they can ask us for tissues. Since 2015, every drug, whether it's a winner or a loser, we've been putting aside 20 or 30 or 40 mice to be euthanized at age 22 months and frozen. And anyone, this is changing next year, I'll get to that in a minute, but anyone who wants those tissues just writes us a note saying, here's what I want, this is the tissue I need, here's what I'm going to do with it, here's my power analysis, and we just send them the tissue. It's clearly a national or international resource. We've sent tissues overseas to other labs to make use of tissues that have tons of useful information in them, but we can't study everything. We can hopefully attract the interest of people who can study everything. This program, which we call CIP, the Collaborative Interactions Program, unfortunately, I think, is going away next year. The National Aging Institute has decided that instead they want to replace it with a new program, which they're calling the Interventional Biogerontology Repository, in which the tissues will not be requested from us. They'll be requested directly from the National Aging Institute. And the National Aging Institute will make all decisions as to who gets the tissues, who doesn't get the tissues, how much tissue they get. I'm not so sure that's a grand idea, but the worst thing is that they will have only once a year call. When people send us a note, we generally can make a decision within 2 or 3 weeks, and they can generally get the tissue within a month or two. Adding an extra year of time for the NIA staff to sort of figure out who gets the tissue or not is not going to speed things up. So I view that as a step backwards, but I'm not in charge of it.
Rich, based on these tissue blocks, what have you learned, if anything, through collaborations with people looking at epigenetic changes in the treated versus untreated mice? I mean, we have to imagine that there's some difference in gene expression, and that would be at least one way to look at it, correct?
Yes, that is one way to look at it. And we have indeed, there are some labs, Steve Horvath, I think, is well established and does lovely work. Steve has asked for tissues, and we have sent him tissues. And we've explained to anybody else who is working on some aspect of either global or localized tissue-specific epigenetic change, we'd be delighted to send them tissues to
has that been done?
I know Steve has done some of that work. I think some of our drug-treated mice have gone to him. Vadim Gladyshev has gotten at Harvard, has gotten lots of tissues from us and has published metabolomic assays, for instance. I don't think any of his epigenetic stuff has come out yet, though I'm not certain of that. The paper that Johan Auwerks just published with Rob Williams and Maroon Bousleiman in Science had some epigenetic materials in it. The problem is that no one at this point knows enough to know what tissue to look at. So it may be that a particular drug is working because it sensitizes the liver to high glucose levels or something. So you'd want to then look at liver tissue or pancreas tissue or islet tissue or fat tissue, or quite plausibly tissue of some obscure cell type in the hypothalamus, which regulates the hormones that make you hungry or not hungry. And sort of I'm going to guess that the liver is important.
Right.
I'm going to look at all the epigenetic changes in the liver is a very crude way of addressing that. In my view, the progress will come when someone says, hey, look, this drug works by hitting this enzyme in this set of hypothalamic neurons. Now let's look at the epigenetic change in those neurons.
Yeah.
But we're not there yet.
So you've already alluded to the aging rate indicators. Say a little bit more about that and how that's factoring into the work.
Everybody is familiar with the concept of biomarkers of aging. And by analogy, it's sort of like the odometer in your car. Your odometer tells you how far the car has been driven, and a biomarker of aging, in a crude sense, tells you how far your body has been driven.
But what would you say they are, Rich? I mean, like what biomarkers do you think we really have of aging? What are the odometers?
Yeah, that's a whole separate complicated issue. I personally don't think we have very many at all.
Yeah, I would agree with that. I don't even think we have the odometer. So but
yeah, I agree with you. But conceptually, you can imagine if someone comes into your test facility and they've got a lot of high affinity antibody and their vision is terrific and they've got no cataracts and they're great at hearing and they can do 100 push-ups and they're great at running up and down a hill and their skin is smooth, et cetera, all 10 or 20 domains, they sort of look like they're 40. You can say, okay, they are biologically young. That's a...
Yeah. Although it's a bit, I mean, I put that in the realm of function, right? So I agree. We have lots of functional tests that give you odometer-like insights. But when you think about a biomarker that is assay-based, I think we're both saying the same thing.
I share that.
There's nothing there.
Yeah. I wasn't attempting to praise biomarkers of aging. I wanted to set that up as a familiar concept, because I mostly wanted to say that aging rate indicators are not that. Aging rate indicators, by this analogy, are the speedometer. They tell you how quickly you're aging and not how far you've gone. So what we were looking for, and in a moment I'll tell you the evidence that we think suggests this is a good idea. We were looking for things that always change in the same direction in every kind of slow-aging mouse. That would distinguish not how old they were, but how rapidly they were going to be aging. So we have 9 published and 1 unpublished slow-aging mice. We have 4 genetic mutants, the SNEL, the growth hormone receptor knockout, the Ames dwarf, and the PAP-A. We have a famous diet, calorie restriction, and we have at least 4 well-vetted drugs, acarbose, canagliflozin, and 17-alpha estradiol, and rapamycin. So we said, let's find something that is changed in the same direction in all 9 kinds of mice. And this is true for a 10th kind, P10 overexpressors, though we've just submitted that for publication. So the next time we talk, we'll have at least 10 mice for which these things are true. And the pleasant surprise is that we now have 13 things that always change in the same direction in all 10 kinds of slow-aging mice, even when they are young adults. And that's the crucial thing. The biomarkers are useless until the animal or the person gets old. They've got to have a certain amount of aging behind them to see if they are young-like in comparison to control untreated people or people with a different gene. You have to wait. The aging rate indicators, because they are measures of speed, you can look even when the animal is young, and hypothetically when a human is a young adult. So most of the work that we've done on the mutant mice was done on animals that were 4 to 6 months of age, and the work on the drug-treated mice was on animals that were only 12 months of age. There are changes that are in famous molecules whose connection to disease is not just fanciful. One of these is UCP1, uncoupling protein 1. It's a mitochondrial protein that allows your mitochondria to burn fat without doing a lot of work. It just turns the fat into heat. It's involved in thermogenesis. And it's long been known that having a lot of UCP1 is something that happens when you do exercise. Exercise increases UCP1, and mice that have a lot of UCP1 live a long time. So it's thought to play a major role in protecting you from obesity, from diabetes, from metabolic syndrome, from some sorts of inflammation. Well, every one of our slow-aging mice has a lot of UCP1 in the white fat under the skin, in the white fat in the abdomen, and also in the brown fat between the scapulae. All 3 of these fat depots have elevated UCP1. The exception to that rule is very informative. You remember two of those drugs, canagliflozin and 17-alpha estradiol, extend lifespan in males only, and UCP1 goes up in males only for those two drugs, which is a strong indication that whatever process is making the drugs slow the mortality rate and increase longevity is the same process, at least in its sex specificity, as the UCP1 story.
And tell me, UCP1, you are measuring that how?
We
how
take
much
the fat and we look at the protein by Western blot.
Okay. How much biologic noise do you think exists in that on a day-to-day basis so let's now talk about a normal mouse, a control mouse on the control diet. If you sample his fat every day for a month, and some days you put him on a treadmill, a wheel, some days you don't, some days he doesn't eat that much, some days he does. In other words, he replicates for short bursts of time some of the activities that might either be associated with a longer life and or associated with a behavior that increases the protein of interest. It would be really troublesome, even if everything you said were true, it would be really troublesome if UCP1 spiked on those days, because then it wouldn't really be a useful odometer, or rather speedometer.
So you brought up three separate interesting issues, and they need to be treated separately. The first is in a normal mouse where you're not making them exercise and you're not feeding them foie gras, if hypothetically you get a little bit of fat from that same mouse every single day or every hour over the day, would there be much change in UCP1? That experiment, of course, can't be done, but it doesn't invalidate our findings, because even if that would introduce some noise, the consistent difference between the mutant mice or drug-treated mice and the controls, the noise is already built in, budgeted into that. If there was a lot of noise, too much noise, we wouldn't see a significant effect of the drug or the diet or the genetic intervention. The second point you raised is, could one perturb this by getting an animal to exercise? And people have done that. UCP1 is changed by chronic exercise, and that's one of the reasons why it's thought to be amongst the mediators of the health benefits that attribute in people and in mice to exercise.
I'm sorry, I was asking a slightly different question on that, Rich, although that's good to know. The question I was asking was, if you took an otherwise sedentary mouse and exercised the hell out of him for a day and checked it, then would you be fooled by an elevated level? And in other words, could somebody cram for the test?
I don't know. There may be some people out there who've done that, but I'm not one of them, and I don't know that literature very well. It's an empirical question, not hard to address, and they already have been done.
Yeah.
And the related question is about time of day. We try to normalize it. That is, our mice are always euthanized between 9 in the morning and 10 in the morning. So it's not the case that some of the mice are morning mice, some of them are afternoon mice, some of them are evening mice. And we feed them ad lib. So that does introduce some variation. Some may have had a early morning snack, and some may have had their last meal 4 hours ago before the lights go on. That also is going to introduce some noise into the measure.
How are the animals euthanized?
Yeah, we use a method that makes them go unconscious within 5 seconds. That is, we put them into a bag, a plastic bag, and then we fill the bag quickly with carbon dioxide gas. They take a few breaths, and within 5 seconds, they're unconscious. And within 10 seconds, they stop breathing.
Okay. So in other words, it kind of minimizes, to some extent, the hormonal stress at the end of life, given that carbon dioxide is highly sedating.
That is exactly why we do it. The American Veterinary Medical Association has recently, that is 5 years ago, made the method we use a suspect method. We still have permission to use it, and we've talked to the vets about it, so we're not violating any of the rules. But they recommend now, I think there's a rotten decision, that mice be placed in a cage and that carbon dioxide gas be added gradually. It takes them we timed this on a batch of mice. to see what it would take. It takes 7 minutes for them to stop breathing or to lose consciousness. And over that 7 minutes, their adrenaline level goes up, as you can imagine. Their glucose doubles. Their blood becomes acidic, right? The pH drops. So we would never want to do that, because who knows what is that doing to all the protein kinases and the metabolites. Anything that is glucose or hormone sensitive is gone haywire there. So we asked our animal care committee, for that reason, could we do it the way that it had been approved for the previous 100 years? Because doing it the new way would spoil all of our experiments. They said, yeah, you're right. Which I think is both more humane and also better science.
Yeah, agree. There's an interesting parallel here with the way animals are harvested for human consumption, which is unfortunate that the way most animals are harvested is very stressful on the animal, and therefore
that's right.
It actually erodes the quality of the food that you're about to consume based on the stressful environment of the animal that's in the way it does.
Yeah, I can see that.
So are there any other candidates besides UCP1 that serve as a fantastic indicator of a speedometer?
Let me just list a few of them, because a few of them are really interesting and exciting stuff. The same woman that did the UCP1 study, her name is Jina Li, which is Li, also looked at macrophages in the fat. There are two kinds. One makes a lot of inflammation, and all of these slow-aging mice, they go down. And the other prevents inflammation, the M2 cells. All these mice, that goes up. So at least in the fat, all of these influences, genes, diet, and drugs, make the fat much less inflammatory. That's likely to be important, because you are fully aware of all of those studies suggesting that a lot of diseases involve inflammation. High inflammation is a sign of stress. It's really bad for you. So it may be that these drugs and diets and genes are working in part by reducing inflammatory tone. Now, in addition, we have looked at proteins in the brain. The two we looked at in the brain, one is called BDNF, brain-derived neurotrophic factor, and it's thought to protect brain cells from stress. The other is double cortin, DCX, which is a sign that the brain cells are making new brain cells. It's a sign of neurogenesis. These go up in the brain in all of the slow-aging mice. Again, the exception being the two drugs that are sex-specific, and here the BDNF and double cortin changes are also sex-specific and seen in males only.
But one quick question, Rich, sorry. The macrophages and M2 were in the fat cell. Was UCP1 also?
Not in the fat cells, in the macrophages in the fat depot.
Okay. Where was the UCP1? Was that in the liver, or was that?
No, we looked at it in the brown fat, in the inguinal white fat, which is subcutaneous, and in the perigonadal white fat, which is abdominal, 3 different fat depots. And the macrophage changes are seen in each of those depots, and the UCP1, which is in the adipocytes, is also seen in all 3 of those depots.
Got it. And I'm sorry, I interrupted you. You're about to say one more.
Yeah, the last one I was to sort of round up. We have many others now, but the last one that's really, I think, thrilling is a protein called GPLD1. GPLD1, it's made by the liver. It's also made by the fat. What it does is there are lots of proteins that are sticking out outside, on the outside of a cell, and the linkage is a specific sugar bridge, glucose phosphoinositide. That GPI bridge, GPLD1 cleaves that, and so it releases lots of different kinds of proteins from cellular surfaces. The reason we thought it was interesting was another lab, Horowitz, had shown, this is just 2 or 3 years ago, that if you exercise, GPLD1 goes up. It's true for mice, it's true for people. And more exciting even than that, if you have GPLD1 go up, cognition goes up. So Horowitz and his colleagues have argued that one of the reasons exercise is so good for your cognitive powers is that it tricks the liver, maybe the fat. They said liver, but we found it from fat also, into making GPLD1, which in an unknown way improves cognition. So what we found now in our lab was that all 9 kinds of slow-aging mice, 10 now, also have elevated GPLD1 production in the liver and amount of it in the plasma of the mice. We can't prove that that's why BDNF goes up in the brain, double cortin goes up in the brain. Some of these mice are known to have great cognition. We can't prove that it's due to GPLD1, but obviously we are hoping that is the case. The reason that the GPLD1 result was, to me, so extremely exciting was that in another part of the forest, another part of the lab, a guy named Gonzalo Garcia was looking on differential mRNA translation, and he had discovered that slow-aging mice, it turns out all of them, have a lot of cap-independent translation. That is, they can pick a subset of the messenger RNAs and translate them in a special way and cause proteins to be made in ways that are independent of the amount of RNA for that protein. Well, we proved and published now that GPLD1 is one of those proteins. It is controlled not by changes in the transcription of the DNA into the RNA, but by the differential translation of the RNA into protein in a cap-independent translation module. So this is our first serious link between the molecular biology of protein translation, Gonzalo's stuff, and the physiological effects like cognition and BDNF, which was Gina's domain. It's really very pleasant to see these two different lines of experimentation sort of get tied together here through the same protein, through the GPLD1 protein.
And tying this back to what we said earlier, this is an example of where, for example, the epigenome might not matter as much, because that presumably would have a greater impact on transcription. And here you're saying, actually, this seems kind of independent of transcription. This is a purely translational phenomenon.
Yeah, let me agree with that about 90%. So the 90% I agree with, many labs just look at RNA levels. Transcriptome biology is relatively easy, and now you can follow it up with epigenetic exploration of what controlled Most of the published omics information is lists of RNAs that go up or down. However, RNA is very poorly correlated with protein, and it's the protein that counts. There's a lovely pair of studies from the Jackson labs. Ron Costanja was involved in one of these. They measured, a lot of this is Gary Churchill's work. They took mice of 4 different age groups, black 6, but what can you do? And they measured the changes in proteins. They made a long list of proteins that change with age. Good. They did it in 2 tissues. Then they looked at the same mice, a long list of RNAs that change with age in the same mice in the same tissues. It turns out that the correlation between the RNA and the protein was 30%. That is, only 30% of the age effect on protein level could be blamed on, attributed to, changes in the underlying transcription data. So if all you've got is the transcription data, which is what most people have, you have sort of blinded yourself to the other 70% of what is controlling protein levels, and it's the proteins that actually do stuff in the cell. I think until people come to grips with that discontinuity, they won't really be motivated to look at the proteins, which are harder to study but doable. And I think it is the proteomic data collection that will be valuable. Our lab has shown that the proteins can be modified. We're not the first to show this, both by differential RNA translation, this cap-independent translation, and Joe Endicott has found that there's also differential degradation, subsets of proteins that are degraded by the lysosomes through chaperone-mediated autophagy. They mold the proteome in ways that are completely independent of the mRNA for the underlying proteins. I think that's a big part of the story, which people are just gradually waking up to.
Yeah, I think this is so important. I'm going to just slow you down, and I want to make sure we go through this again in some detail. I understand what you're saying. I want to make sure everybody does, because I hadn't actually known that fact about the poor correlation between protein translation and mRNA transcription. That's a very big deal.
Yeah.
I would have guessed that to be a much higher number.
Me too.
So can you just go back and give everybody the sort of bio 101 explanation for how we turn DNA into mRNA, into tRNA and protein, where that's occurring in the cell? And, you know, so people, I want people to understand the point that you just made, which I think I wrote down. It's so vital, which is without the proteomic assessment, the story is incomplete. That's to me the takeaway from what you just said.
Not only incomplete, but mostly wrong. So yeah, sure. I mean, you learn nowadays, I guess, in high school that the DNA can be transcribed into messenger RNA. It has the same sequence, more or less, and encodes proteins. That's where epigenetic control comes in. The cells that are made only by proteins made only by the liver are in large part because the liver has turned some transcripts on and others off. The same is true for the eye and the brain, etc. So now each cell has its own complement of RNAs.
Right. Let's make sure people see that point again, right? The liver and the eye and the muscle have the same DNA. Why does the hepatocyte make a protein that the liver needs, whereas the neuron makes a protein that it needs? This is where turning on and off the gene, the epigenome, matters. Okay. So
it certainly does matter. People used to think it was the only thing that mattered, and I think that's probably wrong, but it's certainly an important thing. Many of the differences between the neurons and the skin cells and the blood cells and the liver cells are because they express different messenger RNAs from the same DNA template. It's just like if you have a library of books and someone decides to read the Trollope and somebody else wants to read Emily Dickinson. They have different experiences even though they have the same library to work with. So now you've got a batch of RNAs that you've transcribed selectively depending on the cell. Now you have to make them into proteins, so the ribosome will generally bind to them and churn out protein, and the sequence of the protein will be based upon the sequence of the bases in the messenger RNA. Most ribosomes start this by binding to the very end of the message at a place called the cap, the 5' cap. That's not where the translation starts. That's the sort of start here signal. Then the ribosome bumbles its way down to the place where it's going to start, and then it starts making proteins. So most translation is cap dependent. The ribosome can only find and get working on that messenger RNA by binding to the cap, bumbling down to the start site, and then making the protein. So the default presumption, which turns out to be wrong, is that once you've got those RNAs out there because of transcription into the mRNA, the rest is automated. They just churn out proteins based upon the RNA that they've got. So there are now many studies, and I quoted my favorite ones because they come from friends of mine and because it's related to aging. There are now lots of studies that say the idea that the set of proteins depends only on what mRNAs you've got is really a poor approximation. What Gary Churchill and Rod Corstanja and their buddies accomplished was they actually looked at this in the context of aging in a systematic way. They looked at a tissue like kidney, which is Ron's special favorite tissue. They looked at kidneys of 6, 12, 18, 24-month-old mice, and they made a long list of which genes change at the RNA level as aging progressed. And now they did the same thing, but at the protein level, same tissue, same age, same genetic stock, the same mice as far as I know. And so now they have two parallel lists. And the old-fashioned default assumption would be that if you are on the winner list for age sensitivity for the mRNA, you're going to be on the winner list for the proteins encoded by that messenger RNA. And that was right 30% of the time. Not 100%, but 30%. There were big differences with age in the kidney and one other tissue. I don't remember what other tissue they looked at. There were big differences in proteins as aging went on, but only 30% of those changes were corresponded to the same change, same amount, same direction in the messenger RNA. The rest came in somewhere else. So this could, in principle...
And by the way, is it post-translational? How much of that is
question, and
same
that's
protein?
What I was just going to get to. That's what we don't know. There are a batch of possibilities. I've pointed to differential translation. This is the Garcia's work on cap-independent translation, where the ribosome doesn't care about the cap. It can bind to something else on some of the mRNAs and do those instead, even if the cap is no longer working. So that could be selective RNA translation. Now there's also selective RNA sequestration. The RNA can be hidden and not made available. There's selective RNA degradation. This plays a role. Once the protein has been made, it can be degraded, chopped up into amino acids in many different ways. The proteasome can do that. And Joe Endicott's specialty, there are lysosomes that can take in some, but not all proteins. A fairly small percentage of the proteins get degraded by the lysosome. So there are changes in RNA stability, changes in RNA location, RNA translation, protein degradation of many different flavors that will, in important ways, modify the amount of the protein independent of any underlying changes in the messenger RNA. I think more people learn about the non-transcriptional pathways that mold the proteome, in our case, of course, in the context of aging and anti-aging drugs, but these same principles apply to any disease-specific process, any health process, any drug response. I'm just talking about it in aging terms. Once people buckle down and sort of learn this, they will not devote their entire labs to analysis of transcripts. They'll pay more attention to proteins and also to the subtleties of what happens between transcription of the DNA to the RNA stage and then eventually the stable, steady-state level of the protein.
Well, I mean, there's at least 5. I lost count, right? At least 5 plausible explanations, and none of them are mutually exclusive. So you could obviously have hybrids of these.
Absolutely.
As to all the places where you can, quote unquote, go wrong between transcription and the final protein output.
Or go right. I mean, you mold it, whether it's
fair.
Bad for you or good for you is interesting.
Let's go back to the speedometer, the aging speedometer. Obviously, one of the so you used these 10 known cases of slower aging, right? So 4 genetic mutations that result in slower aging, the tried and true caloric restriction, and then 5 drugs.
It's actually
that have
four drugs.
4, but
because the newest unpublished one is actually another mutant.
Okay. Oh, I see. Got it. So 4 drugs. So you've got these 10 slowly aging phenotypes, and now you've identified consistent, very consistent, even down to sex-specific differences. Is there a dose effect that you're seeing? Because presumably these 9 or 10 phenotypes technically have slightly different lifespans and therefore are slightly differentially aging.
Yeah, so I'll address that question in the context of a battery of things we don't know, want to know, and could find out in the next few years if we're given the opportunity. One of the things we would really like to know is, what about the next 3 drugs? Do they do the same things, do the same aging rate indicators? That's a test of our hypothesis. If the answer is yes, yes, and yes, that is great. If the answer is no, no, and no, something has gone wrong and we need to reconsider the whole foundational idea. Another important area, which is getting closer to what you were just asking, is if you give a drug to a mouse, how long does it take for the aging rate indicators to switch? Mm-hmm. If it takes a few months, that is terrific, because that means we can take 100 drugs and test all 100 of them, not for lifespan, which is really expensive, but test all 100 of them for the ability to switch aging rate indicators. If we test 100 drugs off the shelf, or that some colleague suggests to us, and 5 of them switch all of the aging rate indicators, those are the 5 that are most likely, we think, to be winners for the lifespan experiment. So we could use these as a screen to try to identify drugs that are more likely than not to work in the context of a lifespan experiment. We also don't know how long they stay switched. So let's say we give a mouse rapamycin or 17-alpha estradiol or mystery drugs A, B, and C, and yes, all the aging rate indicators, 8 weeks later, they're at the slow aging level. Okay, now we remove the drugs. Will they stay, the aging rate indicators, will they stay where they are? We don't know that for drugs. We do know it, however, because of a great experiment that we did with Andrzej Bartki. He was the inventor of the Amesdorff mouse. He's the first person who showed they were long-lived. Andrzej had found that if you take these Ames dwarf mice, they're mice that have very low growth hormone, very low IGF-1, and they live 40% longer. He has found, he published this 10 years ago, if you give them growth hormone shots when they're a little baby, just starting at 2 weeks of age, and only for 6 weeks, so we stopped giving them shots when they're 8 weeks old, that's enough to turn off the whole anti-aging program. They are no longer long-lived. We found that they no longer have stress-resistant cells, and we found they no longer have low inflammation in the brain. They go back to normal. So what we did was we got from Andrzej Bartke some 20-month-old mice that were treated, but only when they were babies. So any epigenetic change that happened to them, they'd have to do it in that growth hormone treatment period and remember it for 20 more months. And the answer is that the changes in all the aging rate indicators, easily seen in the 20-month-old mutant mice, they all went away in the mice that had gotten the growth hormone shots in the juvenile period. So the exposure to growth hormone shots by injection for a brief period of time in youth was sufficient to lead to lifelong reversion of the aging rate indicators to the normal, that is, away from the slow aging position. What we want to do now is the inverse of that. We want to give them something good for them and see if we turn them on, that is to slow aging, and then it stays up forever. That's what we're hoping to see, of course. We can also use these for people. That's the sort of next frontier. If you give these drugs to people, do the people change the aging rate indicators? If the answer there is yes, that opens up, of course, a massively productive frontier for aging research in people.
One quick question about the Ames mice. What happens with the reverse experiment when you wait until they are, 20 or call it even 12 months of age and give them growth hormone once they've fully matured? Do you shorten their life or revert their life back to normal?
No, we tried that. My lab failed. That is, we started our shots at 4 weeks of age. We did it in Snell-dwarf mice, which are more or less the same. We started at 4 weeks, and then 3 years later, we had found that it had no effect whatever. It took 3 years for the mice to age. It had no effect on lifespan. So Bartke then did it starting at 4 weeks of age, and he failed too. That made me feel great. We had just messed up. I would have given up. I had given up at that point. Bartke did not give up. He did it over again, but this time starting at 2 weeks. And when you start at 2 weeks, it works. When you start at 4 weeks, it doesn't.
Okay. Going back to the biomarkers, BDNF, DCSF, you're measuring, DCX, I'm sorry, you're measuring those directly in sections of the brain. You're measuring those in CSF. Where are you getting that?
We take bits and pieces of the hippocampus, make a suspension of the proteins, and do a Western blot. It's just measuring the amount of protein right in the brain.
Okay. As you think about the application of bringing this to humans, what would it look like to bridge that gap? In other words, if you wanted to know if this type of exercise routine versus that type of exercise routine, this type of diet versus that type of diet, or your home brew of rapamycin versus not is having a benefit, at some level, we will need to get this out of plasma. It will be very difficult to do this out of CSF or even fat biopsies. How difficult a bridge is that?
I'll tell you about 2 steps we're taking. One of them is a collaboration with Stephen Cummings and Teresa Mao and their colleagues. They have a project at UCSF called SOMA, S-O-M-M-A. They have a collection of several hundred human volunteers, all in their 70s, in good health. These people took a lot of functional tests. How good are they at thinking? How fast are they? How strong are they? And then they allowed tiny, tiny muscle biopsies and tiny fat biopsies. So we have requested, and I think are likely to receive, tiny bits of muscle and fat from these brave volunteers, and we will test. Do those that have a lot of the muscle-specific change, which is a protein called FNDC5, and the fat-specific change, like UCP1, for instance, our prediction is that amongst the 70-year-olds, the really fit ones will be the ones that look as though they have always had youthful aging rate indicators. So that will be one way in humans And we'll have plasma from these same people as well. So that'll be one way in humans of beginning to test internal tissues to compare with plasma. But that's impractical for clinical use. So what we really need now is ways of extending our results to plasma. Two of the things that we can measure, we have measured and published in plasma. It turns out that irisin, which is the product of FNDC5, the thing that goes from muscle to fat, that's in plasma. And in fact, it goes up in all of our slow-aging mice. And the other is GPLD1, which I was talking about previously. GPLD1 is also in plasma, and it also goes up in all of our slow-aging mice. So we'll be able to evaluate that in human plasma samples. But we really want more than that. So one of the studies that we'll be doing in the next few years with Catherine Kazarowski and with a colleague named Kostas Lysiatis at Michigan, he's a metabolomics expert. We will take a batch of mice, healthy, young, het3 mice, the same kind that the ITP uses. We'll take blood samples from them. We will measure the aging rate indicators in the blood, but also in the muscle, fat, liver, and brain of all these mice. And Kostas will measure several hundred metabolites in the blood of the same mice. And our goal will be to ask which 2 or 10 or 20 or 100 metabolites correlate, plasma metabolites, correlate with the plasma and the internal tissue, ARIs. If we can derive from this exploratory exercise a list of 5 or 10 things you can measure in mouse and human plasma that tell you where the ARIs would be internally, that's great. We think it can be done in principle. There's a terrific scholar, younger scholar named Hamilton O, working at Stanford with Tony Weiss-Correa. Hamilton has been able to deconvolute plasma signals by saying these represent changes in the pancreas, these represent changes in the liver, these represent changes in the brain. He's not working in mice yet. I'm trying to twist his arm to get him to do it. But in principle, it can be done. You will be able, we hope, to detect plasma molecules which correlate with tissue-specific levels of ARIs. That will be the bridge to human studies.
Now, is he doing that by looking at cell-free DNA?
I can't tell you for 2 reasons. A, I don't understand it, and B, it was at a Gordon conference, and I'm not allowed to talk about it, but you could call Hamilton, his last name is spelled O-H, or Tony Weiss-Correa, who runs the lab, and maybe they'll tell you.
Going back to irisin or irisin, that is the product from what protein?
Well, it is a cleavage product of a muscle protein called FNDC5. So we do 2 things. We measure FNDC5 as a protein in muscle, and we measure irisin as a peptide or protein in the plasma. And they always, in our hands, go up and down together. All the slow-aging mice have more of the protein in the muscle and more of the irisin in their blood.
There was a study in Nature, God, I want to say it was about 2011, maybe 2012, that made all this promise that it was basically, I think, identifying that irisin concentrations were high in people post-exercise, and the promise of the paper was we now have the exercise drug, right? It was we're gonna just give people irisin, and you're giving them an exercise pill. The temptation, I suspect, for any of these things is the same, right? Presumably, GPLD1 in a pill is something that someone's going to think, hey, that's got to be a good thing. Do you think that's a good thing? And if not, why not? And by good thing, I mean, do you think it's going to have efficacy? Let's take a moral judgment out of that and just talk about sort of clinical efficacy.
Irisin has had a checkered past history. The original papers that said what you just said turned out to be using an assay for irisin that was highly inaccurate in the sense that they overestimated the actual concentration of irisin by a factor of about 100. Not subtle.
That's a problem.
Okay. And people who were skeptical of the original results, they actually worked out a mass spec-based assay for irisin, gold standard, and proved that the original antibodies were not specific enough to be useful to actually measure irisin levels. And so many people who had felt those original papers were highly promising, as indeed they were, sort of discounted the whole system. But it now looks as though they were throwing out the proverbial baby with the bathwater. Now there are good antibodies that are sensitive enough to detect irisin at actual levels. When Gina Lee brought me her irisin data, I said, oh, okay, I sort of believe it, but you know, irisin antibodies have a terrible reputation. Let's look at the precursor protein, FNDC5, in the muscle. And we decided not to publish it until we had both the irisin in plasma and the FNDC5 by Western blot in muscle. And they were paralleling one another so very well that I believe both of them now, because they always came out the same.
And why not just do the mass spec on the irisin in that situation and avoid the antibody?
We're no good at mass spec, and we know how to do Western blots.
Okay. So back to the point, do we think that these molecules are merely biomarkers of all of the myriad good things that these behaviors, drugs, or exercises do?
I will bet you, I don't have any secret inside dope, I will bet you that pharmaceutical companies, thrilled with what Ozempic and its competitors are doing, have devoted tons of money to figuring out whether they can get something like irisin into you in a way that doesn't hurt you and does you some good. Neither you nor I is the first person to have thought of this idea, and I'll bet the farm companies have devoted tons of money into looking at that. I think it's a highly promising area of research, although I imagine a lot of it currently is proprietary. GPLD1 is a protein, and swallowing a pill might not work because it might be digested in the stomach, just like every bit of meat you eat is digested.
But the same is true with irisin as well. It's also a peptide, isn't it?
Yeah.
So these are going to need to be injectables, presumably.
Yes, unless you can come up with a small factor that turns on FNDC5 in your muscles. That's what we want to get. And you know, we have those. They're called anti-aging drugs, right? Rapamycin does that. Acarbose does that.
That's sort of the part here that I'm really kind of trying to wrap my head around philosophically is the wrong word, but metaphysically, I suppose, because on the one hand, we have molecules that are now doing things that are impacting aging at a fundamental level. Again, this is counterintuitive. It's not counterintuitive to me that exercise or calorie restriction induce a longer life in the right model. It's a little counterintuitive to me that rapamycin does, to be completely honest. Like I don't dispute it for a moment because I've seen it now over and over and over again, just as you have. But it's still remarkable to me that a molecule is able to act at a fundamental level of aging as opposed to way, way, way downstream at the in the way that a lipid-lowering drug works, where it works on one disease pretty much, and it works through, one path. And the proof of that is indeed your aging accelerator. That is, in fact, the proof of geroprotection. It almost becomes the sine qua non of a molecule being geroprotective versus simply targeting a disease.
Well, let me phrase that in another way. If you have a drug that extends mouse lifespan, I think that's a critically important step towards making a case that it's slowing aging, but it's not the last step. I would not fully endorse that hypothesis unless someone has shown that the mice treated with that drug, in addition to living a long time, they also retain lots of youthful function.
Yes.
Their muscles are great, their hearing is great, their cognition is improved, their bones are better. We've gone through all those steps for the Snelldorf mice, the Amesdorf mice, for the calorie-restricted diet, for the growth hormone receptor knockout mice. We're beginning to make that kind of a story for acarbose. Our first acarbose paper had grip strength and blood glucose control. We're beginning to make that case for 17-alpha estradiol as well and acarbose. So, but building those cases brick by brick by brick is really necessary to say it's not merely an anti-cancer drug.
That's right.
And something that was a broad spectrum anti-cancer drug. I'll bet people are interested in that, but it's not necessarily an anti-aging drug. To make me happy, it has to be an anti-aging drug, and the evidence has to be effects on many different age-sensitive properties. But we have great evidence now for at least 3 mutants, and the calorie restriction diet, and the methionine restriction diet, and we're getting there for rapamycin and several of the other drugs that came along, 5 years, 8 years after that. So I think there will be a very strong case that these drugs are acting by slowing the aging process and delaying, maybe not quite all, but maybe all of the aspects of aging that make people unhappy about getting older. And I agree with you. It's a fundamental reorientation of instinct. That's what this experimentation is designed to do. It's designed to reset one's instinct on these points.
We've already talked a lot about why the Black 6 mouse has a lot of problems. You've also alluded to the fact that they're basically genetically programmed to die of cancer. What is the natural history of your mice, and how does the natural death of the mice in the control group by cause, we've already obviously talked about length of life, but what is the cause of death in the controls typically versus the treateds in the success cases?
Yeah, two very good questions. The context that's necessary here is that nearly all of the mice that are available throughout the world for medical experimentation come from the Jackson Laboratory, which for 30 or 40 years was mostly interested in cancer. So whenever a mouse got cancer, they kept it. So most of the strains that became the world famous,
they were positively selected for cancer.
They were selected for getting a lot of cancer. So the had 3 mice, has 4 different grandparents, and cancer is the cause of death in about 80% of our mice, but it's varied. Some sort of lymphoid or leukemia cancer, maybe 30 or 35% of the deaths. In the males, pulmonary cancer, liver cancer are both prominent. In the female, it's not pulmonary so much, but breast cancer, liver cancer again, hemangiosarcoma, and then maybe 30% of the mice, if both sexes, die of, 1% will die of this kind of cancer, 2% will die of this kind of cancer, 3% of that kind of cancer. So it's 80% of the time, it's some sort of neoplasia that is the lethal injury. And that's why one could make initially a case that, all these drugs are doing is slowing down every single kind of cancer. That's why we have to look at a lot of things that are not cancer. The second part of your question is, does the proportion of different kinds of cancers or causes of death change in these different mice? And that's a hard question to answer, because when we do a necropsy series at the end of life, which is, you have to do it at the end of life to see what they died of, we usually have only about 60 mice in the treated group and about 60 mice in the control group. So if a particular kind of cancer, let's say liver cancer, kills 10% of the mice, you only have 6 cases. And if that goes up to 9 or goes down to 3, that would answer your question with a yes, but statistically we just don't have enough cases to be confident. Only once did we come across a statistically significant alteration. It could have been a fluke. We had a drug that was extending lifespan in males and females, but it did not increase the age at death of the females dying of breast cancer. So one could have made a case that breast cancer is caused by something that is not related to this drug's anti-aging mode. That's something we're always on the lookout for, but the number of autopsied cases is almost always too small to really have a good grip on it.
Well, that's why I think it makes it very interesting that we're going to see your colleague coming on board who specializes in the neuroscience and the neurology of the mice, because I think to make this truly exciting, we want to continue to see functional improvements. And functional improvements in both strength and cognition would go a long way. And by the way, it also is worth, I guess, asking, I haven't asked you this, but do you know if there are cases of drugs that do not improve lifespan, but do improve, say, grip strength and treadmill time? In other words, are there drugs that are improving health span without lifespan in the ITP that you've documented?
Yeah, this is a chestnut that always comes up, and the Aging Institute in particular is passionately interested in the notion that maybe a drug will make you healthy and then you'll drop dead right on schedule. The answer to your question is no one has looked for it, and that's because in our phase 1 assays,
Yeah, it's too much work. Yeah, you can't do it.
We don't do it. We only do those detailed studies on things that extended lifespan. The reason that things extend lifespan is basically it postpones all the bad stuff that lead to death. So to do it, we could screen a lot of drugs for age-sensitive variables in the hopes that we would find one that made age-sensitive variables go away but didn't have any effect on lifespan. I'm not so sure that we would find any. It's trivially easy to do that. If you teach a mouse to do push-ups, you will postpone age-associated changes in muscle mass and muscle strength. And if you teach them they won't get food until they solve a maze, they're going to get pretty darn good at solving that maze. So system-specific postponement of age-sensitive outcomes is not too hard to achieve. It's not really relevant, I think, to the issue of what you can do to postpone all the aspects of aging together.
Let's pivot and talk about one of the successes of the ITP that still somewhat perplexes me. You've already alluded to it several times, which is 17-alpha estradiol. So I'm pretty sure I asked you this question last time, but I will ask you again. Remind me the difference between 17-alpha estradiol and 17-beta estradiol, which is the estradiol that is the dominant form in both males and females. Like we're rolling around with lots of 17-beta.
Traditionally called estrogen. Yeah. So the 17-alpha estradiol is just the same chemically as the 17-beta, except for one of the bonds, instead of pointing up out of the plane, points down in the opposite direction. So it's a stereoisomer. Same chemical formula. All the atoms are attached in the same place. It's just that two of them are pointing up instead of pointing down. And because of that manipulation, it doesn't bind very well to the traditional famous estrogen receptors. So it's doing something. It's got to be binding to something, but it probably is not the traditional estrogen receptors, or it might be that plus something else to get an effect on estrogen-sensitive tissues. You can do it with 17-alpha estradiol. You just have to use a lot more. I think tenfold more is what Jim Nelson found when he did that titration.
And what was the rationale when this was proposed to the ITP? What was the scientific rationale for why this would be a
Jim
geroprotective?
Simpkins recommended it. He's a steroid physiologist, neuroendocrinologist. He reasoned, and a lot of this was wrong, but this is the rationale. Estrogens are good for you. That's why females live longer than males. Let's find an estrogen we can give to males. We don't want to give them 17-beta estradiol because they'll turn into girls and they won't like that. No one wants to be a girl. So let's use 17-alpha estradiol because they won't turn into girls. It does not turn on secondary sexual characteristics. Maybe it will do all the good stuff that estrogen 17-beta actually does. That was Jim's argument. Very plausible. Now, it turns out that if you give 17-alpha estradiol to male mice, it pushes their lifespan way beyond females. It's not merely mimicking the good stuff, if there is good stuff, that estrogen 17-beta does in females. If so, it wouldn't go much further than females are, and it goes well beyond, significantly beyond normal females or drug-treated females, because the drug doesn't affect female longevity at all. What it binds to, in which cells, in which tissues, what it's turning on biochemically is at this point quite obscure. There are at least two labs that I know of, Mike Stout's, I think Mike is now in Oklahoma, and my former student, Mariana Sadigursky. Mariana is at Wayne State. They've published some really nice papers getting at the issue of what is 17-alpha estradiol actually doing physiologically, what does it bind to. Mariana, her last three papers and her just awarded grant are focused on what 17-alpha estradiol does in the brain, what it does to estrogen-sensitive and estrogen-insensitive parts of the brain. So there are a small number of labs, I wish there were more, that are diving into that question. What is the target? What is the receptor? What is the physiological effect? And the more people that work on that, I think the happier we will be.
And again, there's no 17-alpha estradiol is as potent in males as rapamycin?
I'd have to double check. I think it's about a 19% increase. Don't quote me on this. I need to look it up.
Okay. We'll have it in the show notes.
Something around there in the optimal dose in males. and the original dose of rapamycin is there or slightly below that. We now have a better result with rapamycin. When we combine it with acarbose, we can kick the male lifespan up to 29% increase.
Unbelievable.
That's our winner. It's the first time we've
simply unbelievable.
It's the largest percent increase we've ever gotten, and also it's the first time we've gotten an increase by combining two drugs together. So that's the best we've been able to do, and so far we can't get 17-alpha estradiol up to 29%, but I think we can get it up to 19%.
Have you combined 17-alpha estradiol with rapa yet?
What a good idea! We're testing that now. Yeah.
Are you? Okay.
Yeah.
Nice.
I mean, several other groups are testing it also, because it is a good idea. I'm not making fun of you. It is such a good idea that we're trying it, and I know of at least one startup company that's trying that as well.
I mean, again, there's something about this 17-alpha estradiol story that is so fascinating to me. One, there's the total lack of clarity around the mechanism of action, and then there's this sex difference, which can't be attributed to any mimicking of 17-beta estradiol, given the two facts you mentioned, that the males leapfrog the females and the females accrue no benefit. You know, I guess I'm a little bit disappointed to hear there are, I guess only Mariana and Mike working on this problem.
There may be others.
Okay.
I mean, those are just friends of mine that I know of. There may be others as well. I don't know the literature well enough to tell you. I can give you an insight into what we thought was going on with the 17-alpha estradiol and how badly wrong we were. Mike Garrett, whom I've mentioned earlier, he collaborated with a guy named Mo Jain to look at, among other things, steroids in the tissues of mice treated with 17-alpha estradiol. And he noticed something really interesting. He found two steroids. They were members of the estriol family, not estradiol, but estriol, that were elevated at least 20-fold in males that got the drug. And they were not elevated in females at all. It was a male-specific production of estriol when 17-alpha estradiol was given to the males. And we knew it was sex-specific because if he castrated the males before the drug, you didn't see the estriol production. The conversion from estradiol to estriol depended upon testosterone or some other testicular hormone. So we said, okay, great, we've got a winner, estriol. That's going to be the one that is going to work in both males and females. That's the active ingredient. And the data set that's 90% complete, and we'll probably start writing it up in a month or two when we have 90% of the mice dead, but we have 50% of the mice dead, so we've presented at meetings and I'm allowed to talk about it, says that guess was partially right and partially wrong. The hydroxy version of estriol is great for males. It's actually at least as good as 17-alpha estradiol. We won't know till we have the last few deaths, but it's terrific. That was a good guess. You don't need 17-alpha estradiol because the estriol works terrific. However, we thought it would work in females, and it is the first drug we've found that diminishes lifespan in females. So the idea that it would work to benefit females was wrong. It is, for mysterious reasons, harmful in females. So we really don't know yet why 17...
And to be clear, this is just straight estriol,
It's a
E3.
16-hydroxy estriol.
Okay. Why did you pick 16-hydroxy as opposed to 4-hydroxy, 2-hydroxy, or just pure estriol? Was that because that's the only one that went up with the administration of 17-alpha estradiol in the males?
This is a very good question, and you've stumped me. I don't know the answer. Mike Garrett, who told us which estriol to buy, does know the answer, and we could ask him, but I don't know what prompted Mike. Maybe it was commercial availability, maybe it was prior studies of toxicity in mice. Mike has his reasons, and I read the application 3 years ago, and I don't remember what specifically led him to suggest this compound. It wasn't, just stab at the Sigma catalog.
What did the female mice that are dying at an accelerated rate? Yes. Anything specific about this, the manner of death?
We don't know yet.
Okay.
We don't know yet. We haven't done any necropsy.
Okay.
We'll have to do that.
Let's talk about a couple notable failures in the ITP, i.e. drugs that everybody thought were home runs that didn't pan out. I guess the three that come to my mind are resveratrol, metformin, nicotinamide riboside. Any others that should be on that list?
Most people who suggest a drug think their drug is going to work, but I think the three you've pointed out are the ones that have gotten the largest numbers of notices in AARP bulletins and on social media and at the conventions where people want to mingle with snake oil salesmen. So they are certainly the most famous. And I think there's a different level of enthusiasm for each one of them. Metformin, I think, has been very sensibly proposed as a potential anti-aging drug in people. I don't know enough about its benefits and side effects. I know that you yourself have 10 times more information about this than I do, but a case has been made because it's so very safe in people that it could be used in people to postpone aspects of aging. I can see reasons not to believe that, but at least you can make a case for that. It doesn't seem to work in mice. The ITP showed that it didn't work in mice, and now several other groups have confirmed that result. Rafa de Cabo at one point claimed that it worked in mice, but he used a very weird statistical test, and I suspect that if he had used the standard statistical test, it would have failed in his lab as well. I haven't seen the data, so I'm not sure of that, but that's my guess. Resveratrol was hyped for many years. People, often with commercial interests or who had a grant or who wanted to get a lot of money for a clinical trial, would start their talk with a beautiful bottle of red wine and then say resveratrol is in red wine and sirtuins are important and resveratrol influences sirtuins, and just take some of my resveratrol or sirtuin activating agent and you'll live forever. None of that was right. I mean, it's been shown very clearly now that the amount of resveratrol in red wine is, to get enough of it, you need to drink 30 bottles a day. Its status as a sirtuin activator has been questioned by very serious and skilled biochemists. The original data on worms has been disconfirmed by a couple of very good labs. So it was mostly hype. People made a lot of money by selling companies that had an interest in sirtuin activators. We tested it because the director of the National Aging Institute, Richard Hodis, for the first and last time said, "You will test resveratrol or you will not get any money this year." We said, "Yes, sir, yes, sir." So we tested it. We checked with David Sinclair and asked David, "What is the concentration we ought to use?" He said, "Use this concentration and this concentration." We said, "Sure, we'll do it your way. Let's find out." And it didn't work. And subsequently, many groups now, including groups that Dr. Sinclair is associated with, have shown that it doesn't work to extend lifespan of regular mice. The famous paper was one in which the mice were poisoned with a 60% coconut oil diet, and they weren't dying of aging. They were dying because their liver swelled up to the point that it crushed their lungs, and they couldn't inhale. They couldn't breathe. This is not, I believe, a pretty good model for the aging response. So I think the evidence that resveratrol by itself should have been tested was quite weak, and the evidence that it works is very bad. It almost certainly doesn't do anything, at least in mice, in terms of aging. An anecdote.
Does it surprise you how ubiquitous resveratrol supplements are still on the internet?
No,
I mean, you go to Amazon.
I'm sorry to be cynical. Yeah. People are very easy to fool. It's easy to come up with 8 or 10 things that people believe because they read them on the internet or they watched them on Fox News or whatever, and they're just wrong about this. But people are very, very gullible. The anecdote about resveratrol that I think is gives you a sense of what that time was like. I had a friend, a neurologist at Michigan, who had been given a huge grant to give resveratrol to Alzheimer's patients or at the early stage to see if it would slow Alzheimer's. Tons of money. And he came around to a meeting of resveratrol biologists. I was attending it. And he asked people what dose to use. And the range of suggested doses as milligrams of drug per person per day ranged over 1 million-fold. That is, among the experts, the world's experts on resveratrol, the consensus ranged from 1 to 1 million as to what dose was the most logical one. So this is a sign of a field that is making it up as it goes along. NR is the last of the 3 drugs that you mentioned.
Yeah.
I had high hopes.
So probably more hype with NR than resveratrol, truthfully, on some level.
Somebody's making a lot of money.
Yeah, many people are.
Yeah.
So tell us about the findings and what it tells us or doesn't tell us.
We tested it and it didn't work. That is, it didn't extend mouse lifespan. Some people said, oh, well, you have to use NMN, a metabolite. That would have a more bioavailability and better profiles, and this is reasonable. And if someone makes a good case that we should test NMN, and we could afford it, the commercial sources are expensive, we would probably test that as well. I think the notion that
I would have to imagine that some commercial party would donate the drug at this point, right?
We are in negotiations with one such company. Yes, I'm hoping you're right. I'm hoping we could accomplish that. So I'm not a non-believer. I am a non-believer for resveratrol. For NM and the whole nicotinamide modulating family, I think the book is still open, and there's a reasonable chance that some really good stuff could come out of that. It might be that you'd have to give an enzyme that modified the an inhibitor of one of the metabolizing enzymes, or a different form. I have a colleague who has suggested, I don't know if this is public yet, but there's someone who suggests that NR may work in combination with another drug. And his ideas are good ones, and they've been accepted by the ITP. We're going to try the NR plus something else that this colleague has recommended to us. So although NR by itself did not extend mouse lifespan, it could be that some other trick will lead to physiologically important modulation of NAD availability in some cell of interest. It could be that what counts is changing the availability in a cell in the hypothalamus, or in the pancreatic beta cell, or in the lymph nodes or something, finding a dose that is appropriately good for the cells that count but doesn't produce side effects in other cells. May be tricky, but it might work. I'd love to test other things in that general nature. And of course, I mean, it goes without saying, I should have said this earlier, the fact that something fails in mice doesn't mean it's going to fail in people. Testing it in people is going to be much harder. It's easier to sell stuff that's untested. But in principle, one could actually test it in people and see if it does anything good. I'd love to see someone do that.
Well, that's why I think with those three failures, if I'm going to sort of summarize your point of view, I think the failure of resveratrol in the ITP, I think you view as dispositive that drug never worked in any circumstance, anywhere. It doesn't work in humans. It doesn't work in mice. And you just demonstrated that more.
Well, our evidence is not dispositive. That is, it could be true that it doesn't work in mice, but it works great in people. Or it could be that it would work in mice at a 20 times higher dose.
Well, I mean, but I think your point is the plausibility for that is very low, given that it fails over and over and over again.
Building the case that resveratrol has been overhyped. If you look in detail at the evidence suggesting it has health benefits, most of those studies are unconvincing, and many of the ones that are convincing were submitted by people who are trying to sell something.
And by the way, even putting that aside, it's the only study that's really convincing is the one you described with the force feeding of coconut oil. So that's sort of problematic. What I hear you saying with NR and metformin is, even if we repeat these studies over and over again in ITPs, which you won't directly, but you will potentially in other combinations, you have more faith in the possibility that those could still be viable in humans.
Yeah. I mean, the theoretical case that metformin might be good for you, that's plausible. It's not completely proven, but it's sensible. And the same is true for things that are attempting to rescue age-associated changes in NAD. I'm no expert in either of those fields, but the little bit I know is consistent with what these sponsors are saying. There's a good plausible case. We get, as I said, in a good year, 20 or 25 applications for 8 or 10 of them. There's a good plausible case to be made that this drug deserves testing, and most of those good plausible cases yield negative results, and that's expected. That's one of the nice things about aging rate indicators. If they work, if they are flipped by drugs in a short period of time, then we hope our hit rate will, right now it's about 10% give us big effects and a total of 15% give us significant effects. If we can get that up to 50% by pre-screening with aging rate indicators so that half of the drugs we throw into lifespan studies actually give a lifespan benefit, that would be nice.
So Rich, I don't know if you know this about me, but I don't know, 15 to 20 years ago, I used to spend an awful lot of time on boats. Now, these weren't big boats. These are typically small boats. So these are kind of 30-foot boats where you're out in really, really, really rough water. So hours and hours. I don't know how many hours of my life I've spent out in, 30, 40 miles off the coast of California, getting thrown around like crazy. And I was pretty lucky. I've only been seasick once in my life, which when you consider the amount of time I've spent out there, I consider pretty fortunate. But most of the people I spent time with out there got seasick a lot more. And one of the drugs that people used to take care of their seasickness was an over-the-counter drug called meclizine. So I would occasionally take it. I didn't take it that often because, again, I almost never got seasick. But sometimes just to be safe, I would say, you know what, the water looks unbelievably rough today. I'm going to take my meclizine over the counter. Boni, I think, is the brand name. B-O-N-N.
B-O-N-I-N-E.
Boni, yeah. So why am I telling you this story, Rick? I'm sure the listener is wondering, why is Peter bringing this up?
I have an answer for you. I'm spending 2 weeks in December in a small boat, actually, off the coast of Chile. We're going to go up and down the archipelago doing photography, and the seas there can be very choppy, and we've been told to take meclizine or some other anti-seasickness remedy so that we'll be able to photograph to our heart's content without feeling ill. And meclizine is also included in the latest paper for the ITP, which also makes it of interest. The paper that we've just submitted, it hasn't been accepted yet, but again, because it's complete, I'm allowed to present it at meetings and talks like this. There are two drugs. One is meclizine, one is astaxanthin, which in males led to a significant increase, about 10%, in the lifespan of the males. Meclizine was suggested to us by Gino Cortopassi. He knew that rapamycin was good as an anti-aging drug, and it was a TOR inhibitor. So he took several thousand FDA-approved drugs, and in a tissue culture assay, he said, which of these inhibit TOR? Maybe a safe drug that inhibits TOR could find a place as an anti-aging remedy. And at the top of his list, to everyone's surprise, certainly his, was meclizine. It was famous as an antihistamine and also has mysterious CNS effects, which is why it's so good for seasickness. It wasn't, I believe, known as a TOR inhibitor, but Gino found that it was. And so he suggested that we test it, and it does indeed lead to, at the dose we used, a significant increase, about 10%, in lifespan of the male mice. It did not affect females, so we're going to try it again at higher concentrations and see if we can get that to go. We haven't proven that the effect is mediated by TOR inhibition. It has a lot of CNS effects, and maybe the good stuff that it's doing to the male mice is unrelated to TOR. Maybe it has to do with changes in serotonin or histamine production in some critical nucleus in the brain. We need to now look at that. But that's the cool news. The other thing that same paper has, there are 2 points of interest. One is astaxanthin. Astaxanthin is also available over the counter. You can buy it in your local drugstore. It is alleged to have health benefits, but they're all over the map, and I can't assess the strength of the evidence for health benefits. It's also alleged to have many different physiological effects, like an antihistamine or an anti-inflammatory or an antioxidant. It's been alleged to do a little bit of everything. But there's a company in
And it's a food dye, isn't it?
Yeah, it's famous. We eat it all the time. It's famous because it's what's turned salmon pink. The reason that if you want to make your farm farm-grown salmon pink, you dump tons, dump truck loads of astaxanthin into the water, and the salmon turn pink. It's not that you dip the salmon into astaxanthin. The natural salmon eat a lot of crustaceans which have this stuff in their shells, and you can mimic that effect in farm-grown salmon by giving them synthetic or naturally derived astaxanthin. In any case, there's a company in Hawaii that believes it might have health benefits, and they asked us to test it, and we did test it, and that also has a significant effect, and also it's males only. So this paper hopefully will be accepted soon and out for people to judge the strengths of the evidence. Neither of these led to a change in our measurement of maximum lifespan, this test of percentage of live mice at the 90th percentile. It's possible that at a higher or maybe even a lower dose, it might have done that. We're going to need to go back and do a more complete dose response curves. The reason this paper is, I think, likely to be of particular interest to the general public is that it is the first time we've gotten winners that you can buy without a prescription, over the counter. They're not as strong in terms of lifespan benefit as the 4 drugs we were talking about earlier on in our discussion. But, and of course, we don't know if they will work in humans at all. But the position of the FDA that you can't test a drug claiming it has an anti-aging effect will be of less relevance if some of the over-the-counter non-prescription medicines actually slow aging, first in mice and then maybe also eventually in people. I think that's an interesting political and legal question. In terms of the science, we now need to figure out what is astaxanthin doing, and is meclizine acting through TOR or through some other target. It opens up, as any new drug does, it opens up new possibilities for mechanistic exploration. You can bet we're going to be looking at the aging rate indicators in tissues from meclizine-treated and astaxanthin-treated mice.
Well, Rich,
the last thing in the paper that many people will be interested to know is we've tested fisetin. This was suggested to us by Paul Robbins and Jim Kirkland and Tamara Ciconia and their colleagues. Fisetin is undergoing a lot of human trials because of claims that it is a senolytic drug. There are some people, though I am not in that group, who think that there's such a thing as a senescent cell, and that you get a lot of them when you get old, and that they're bad for you, and that a drug that removes senescent cells therefore will be good for you. I'm not convinced, but this is a very popular line of thought. So fisetin was given to us as a drug to test the hypothesis that if you remove senescent cells from mice by giving them fisetin, they would live longer. I thought it wouldn't work, but it was a very reasonable and important thing to do. So we gave fisetin 2 different dose regimes suggested by Dr. Kirkland. He had found in his lab with his kind of mice that they did work at this dose, so that was good news. We thought we were trying to replicate his stuff in our mice at much larger scale, and the take-home messages were 2. First, it had no effect whatsoever on lifespan of male or female mice using either of the dosage regimes that Dr. Kirkland recommended. However, that is not dispositive, because it turns out it didn't remove any senescent cells either. What we can do is there are quite a number of surface markers like P16 that the senescent cell gurus say, this will tell you whether you've got senescent cells. They do go up with age. They go up with age, and we looked at 3 different tissues. That is Paul Robbins' lab and Jim Kirkland's lab. We sent them tissue. It was blind, so they wouldn't know which ones were controls and which ones were treated. They sent us back this number of beta-galactosidase positive cells, this number of P16 positive cells, this amount of P21. And when we unblinded it, there was no effect of fisetin on brain, on liver, on muscle, on kidney, at either lab for any marker that we looked at. So we thought we were testing the notion that removing senescent cells would be good for you. And it turned out we were testing the notion that fisetin removes senescent cells. Now, maybe it works in people. This is not my area, but our colleagues were disappointed, and I can understand why they were disappointed in both results.
Rich, say more about your lack of belief around the role of senescent cells. You made it sound like you don't believe in senescent cells. I assume what you meant, was that actually what you meant, or did you mean you don't believe that senescent cells drive aging, or that you don't believe removal of senescent cells slows or reverses an aging phenotype? Let's say a bit more on that whole thing.
I'm in a slightly awkward position because to tell you the details of why all that is true, and the details require,
just don't say you'll have to kill me if you
that.
tell me. That's the only thing I don't want to hear.
No. I don't do that. It's a long story, but let me give you an analogy. If someone says, "Do you believe in stress?" The answer is sure. I believe in stress, right? But that doesn't end the conversation, because there's the stress of being about to undergo a tense podcast discussion, or the tension of having to give a talk before the National Aging Institute's committee, or the stress of dental work. I hate dental work. Or the chronic stress of being locked into a marriage or a job that you really hate, or getting a diagnosis of cancer. Or dropping a bit of a poison into your GI tract. All of those produce stress, but they're radically different things. They produce different physiological effects. And to say, do you believe in stress, or is this caused by stress, is a way of blinding yourself accidentally to the critically important distinctions. So, do I believe that there is such a thing as a senescent cell? Yeah, if you take human cells in culture, they stop dividing, and those have been called senescent cells. They exist. No question about it, and they're caused by telomere shortening. Now, if you take another kind of cell and you zap it with X-rays, you get a different kind of cell. They make different proteins. They don't have telomere problems. People have referred to those as senescent cells. If you have cells that when you get older, they have P16 on them, people have referred to those as senescent cells. And by saying that this drug removes senescent cells, they are hoping you won't begin to think about the vague definition of what a senescent cell is. In laboratory A, these proteins are called the senescence secreted proteins. In lab B, it's 2 of those plus 7 more. In lab C, well, they don't see those, but they do see changes in the nucleolus, which they view as senescent. So I believe that there certainly are cells that accumulate in mice and in people when you get old that do stuff that's bad for you. Some of them might make this set of cytokines. Some of them, maybe they can't divide anymore, and that's bad for you. Some of them may even have 2 of these problems together. Maybe some of that is changed because RAS has been mutated or DNA has been damaged or something. And exploring what causes those things, how they become bad for you, whether removing that cell type is good, I think that's wonderful. Now, if you say, these are senescent cells, I've got a drug that removes senescent cells, you are skipping all the interesting stuff. That's my view.
Got it. So it's as much a lack of nuance and a semantics issue as it is potentially, or even more so than a biology problem. And when people talk about senolytics, you're saying, hey, we can't really talk about senolytics without understanding which senescent cell you're targeting or which secretory product of senescent cells you're targeting.
That's a part of it, although the problem is much deeper than that. Let me tell you a story. There's this famous paper. Judy Campisi was the key author.
Yes, of course.
She measured the number of senescent cells. This is the paper that introduced beta-galactosidase as the way to count senescent cells. And she looked at the skin of a lot of people, young and old people. And she counted the number of senescent cells and proved that it went up a lot with age. That was a very influential paper. If you look at the paper,
she's at the Buck Institute, correct? If I'm not mistaken.
Dr. Campisi, yeah, Judy is, I believe, at the Buck Institute. Yeah. So in this original paper, which was many years ago, the scores were 1 plus, 2 plus, 3 plus, and 4 plus, not actually a percentage of cells that were beta-gal positive in the skin sections. And only one person was 4 positive. It was a 90-some-year-old grandmother. Well, the actual cell counting was done by a friend of mine, Monica Peacock, who is a dermatopathologist. We were all at BU at that time. So I called Monica and I said, okay, Monica, so 4 plus, how many cells do you have to get to be 4 plus? And she said, yeah, that's 10 to the minus fourth. That is, the skin section that had the highest number of beta-gal positive cells had only one positive cell
per thousand,
in 10,000.
or per 10,000, yeah.
1 in 10 to the fourth cells. Everybody else, all the 70s, 60s, 50s, all of those people had fewer than 1 cell in 10,000. So the statement is literally true. Senescent cells go up with age. These people wouldn't make up the data, but they did emphasize the fact that even in the very oldest sections, the oldest people, the number of actual senescent cells was really quite small.
By the way, what was the difference between the 10 to the 3s, the 1 plus, 2 plus, 3 plus? Because clearly those numbers don't refer to log differences. So
I don't know.
That would be worth knowing.
I don't know.
Right? I mean, because if it goes from
pathologists,
if it goes from 1 in 100,000 to 1, if there's a log fold jump between every group, you could argue maybe there's something interesting, but then at that point it's pretty hard to count.
That was the high limit. I mean, the take-home message here is that senescent cells, at least as indicated by that one marker, beta-galactosidase, are so rare that they're virtually absent from the skin of people of any age. That is, virtually absent, I would consider 10 to the minus fourth and lower. But it's been a very influential, I believe, much overly emphasized, over-influential concept. So I was hoping we would show that fisetin would remove senescent cells from mice and that it would have no lifespan effect. That was what I was betting on. But in fact, that didn't seem to actually remove P16 or P21 positive cells from any of the tissues that we evaluated. So we're back at square one.
So we're still back. What we have learned is that fisetin doesn't do jack. What we haven't learned is if removing senescent cells is or is not beneficial.
Yeah. And it might work in people, you know. Jim Kirkland believes, and he could be right, that you can get it to work even in mice if you administer it as a bolus dose, a huge dose once a day rather than gradually in the food. That's reasonable. He might be right about that.
There's another very popular anti-senescent drug out there. God, it's a chemotherapy actually. Begins with a D. Anything ringing a bell? I'm blanking on the name of it.
Yeah, there's a combination. People often give quercetin plus dasatinib.
That's the right. Yep. Has that been proposed yet as part of the ITP?
Yes, and I can't discuss it because we're not allowed to discuss anything comes in except the things we accept. It was not accepted.
So it sounds like we have a lot to catch up on in a few years. We're going to need to do a rundown on the repeat studies of 17 alpha estradiol plus rapamycin. We're going to need to understand the tier 2 studies of meclizine and the
astaxanthin.
Correct. And we're going to also have to see how they validated against the aging indicators as well. Presumably, we'll also have a little bit more insight into the cross-bridge or the link between the aging indicators and plasma biomarkers that may start to bridge that gap towards actually assessing interventions in humans. So I guess there's no shortage of stuff we'll have to catch up on, Rich.
Yeah, I like that whole list, and I would add one point to it that we touched upon a little earlier. I'd love to know whether these drugs slow cognitive failure, of course.
Yep, that's right. I think the addition of your colleague now coming on board for all tier 2 studies to have a cognitive component, I think is incredibly exciting. Again, I think this point about really understanding healthspan fully can't be overstated. Some might argue even more important than lifespan.
One of the nice things about this program is that it's designed merely to not merely, but one of the things it's designed to do is to stimulate work in other labs. There are a lot of labs that are really good at cognition or heart failure or bone failure. We send these people tissues all the time. Papers have begun to appear showing that the drug does this or it fails to do this or whatever. So the hope is that for every paper we publish with a new drug that works, this will trigger work in a couple dozen labs using that drug either with our tissues or with their own tissues, and that some of those will come up with disease-specific indications, disease-specific functional benefits. The ITP can't do everything by itself, but we're really hoping that publicization of our results will trigger others into doing good work. One of the reasons I was so pleased to be invited back to speak with you was that the last time I was invited to speak with you was the most productive interaction I had had, not just in the sense of how enjoyable it was to chat with you, but also for several weeks after that, I got a lot of people writing to me saying, hey, here's a good idea, and often it was a good idea, or let's collaborate on this, or can you send me this tissue, or, it was this particular podcast is listened to by a lot of smart people who pay attention to what is going on, and that's a major resource. So I'm glad that you invited me. Thank you.
Well, I would echo that, Rich. I mean, we certainly don't have the largest audience on the planet, but I would argue we have the most intelligent and the most curious, and also those who participate a lot. That's the other reason I asked the question about other mechanisms for funding. Again, I think it's a remarkably paltry sum that is spent on this when you consider the utility that can come of this, especially with some of the other. I don't want to use the word ancillary because that's almost disparaging in the sense, but these other sort of accretive tools that are being bundled onto it, such as the neurocognitive assessment and the aging biomarkers. But I really see this as a very important program that even when you include the indirect cost is a $4.5 million program per year. There are lots of philanthropists out there who would happily put their dollars to work if they could double the throughput of these molecules and the biomarkers and the insights. So I know that there are going to be people listening to this who are probably going to say, look, I'm kind of interested in doubling down on some of that funding. It's probably it's a higher ROI than giving a couple $1 million to a university to put an endowed chair in place. And so anyway, I think a lot of good, and I'm hopeful a lot of good comes from this.
Good.
Well, Rich,
that would be nice.
Thank you again. Always enjoyable to speak, and enjoy your trip tomorrow, and not to mention your trip to Chile later on.
I'll send you a picture.
I know you will. I can't wait.
From the boat.
Thanks.
Bye-bye. Thank you.
Bye, Rich.